Let's see if we're streaming on my first ever goofy streamy thing. Alrighty. Let's cut off my feedback loop right here. And I do appear to be online. Better share this to the world. So let's do a share. All right, I'm going to send this out. We'll start in just a minute if you're watching. I'm just putting out a little bit of information so people look. What they're doing. Mew, you get back. Lab assistant Mew is attempting to break into the lab. Bad Mew. Alrighty here. So let's see how this is going. Almost at 10,000. And there are people watching. Yay, people watching. Okay, I think it's getting about time for us to start. I think it's about time for us to start. I see a couple people. Necromorph Biatch. Weird Sisters. There we go, Wider Sisters. Yeah, I suck at these kinds of things. By the way, this is not going to be my first one. This is going to be like my test demo one where I do stupid things and get it all wrong. My first official thing is going to be, technically speaking, this Sunday, which will be a model kit. This is me just attempting to see if I can even do this to start with. So I'm going to give this another 3 or 4 more minutes, and then I'm going to get into it. So before I do that, let me just start off with a couple basic things, and I'll leave you with my background with the Polymaster, which is running right this second while you look at this. By the way, just for the record, you'll notice my background is 0.05 micro sieverts per hour. A sievert is 1 joule of energy per every kilogram of matter, more or less. It's not exactly right. That's actually a grade, but there's a few qualifying factors, but close enough. So not too much background radiation, 6 counts per second, virtually nothing on the neutron channel. It's pretty normal for me. And I'm 2 feet from 2 radioactive sources. So as you can see, distance is one of those great things that really stops the radiation. So if I take the Polymaster and move it right over to where I'm testing and put it right by the tester, what's it do? Let's see what it does. Holy crap, look at that. It's like 3 or 4 inches away right this second. Keep in mind, this is the difference between just a couple of feet. Isn't that quite impressive? Look at it go. Look at it go. If it sees anything on the neutron channel, that's probably not accurate. Lithium 6 iodide europium dope detectors can do weird stuff. Hey, do me a favor, you folks that are watching this, respond back and let me know, please, if you can hear me. If everything looks okay. This is my first shot, so I don't know what I'm doing. Go ahead. I'll wait to see. I've got like a delay on there too, so it's easier for you guys to handle as opposed to being aggressive in my streaming. Nothing yet. Okay. I can hear you perfectly. Absolutely beautiful. Now, the second part is this. I want you to tell me if you can hear this nuclear source. Tell me if you hear a weird sound. Do you hear a really weird sound right about now? Like a woo woo woo. Okay. That's the sound of my Gamma Spectrometer turning the sound of radiation into, well, sound. Alright, so let's get into it now. I think we're about ready. And let's start with what we have here. Now, as you can see, I have my microphone, which I'm talking to you with right this moment. And then I have my line in. The Gamma Spectacular comes from B Research. By the way, I'm going to look over at the chat every 2 or 3 minutes and answer questions if you have any. And by the way, this is informal. This isn't like some kind of class. I'm not, a certified professional or something. So Ask me stupid stuff. That's perfectly fine. This is not some like class. You can just ask whatever, talk about whatever. Blah, blah, blah. The only thing that's going to get you knocked out of here is if you're like some kind of epic troll, in which case I'll hit like the eject button on you, but that's about it. I'm pretty First Amendment friendly, so as long as you're not like a bigot troll, like hitting all kinds of stuff, you're probably not going to have too much trouble. I'm not like epically PC. Uh, yeah. So anyway, I had the line in coming out of the Gamma Spectacular. The Gamma Spectacular is about 300 bucks, and it basically what it does is it takes the pulses of energy that come out of the spectrometer, well, out of the scintillation probe anyway, and it converts them into little sound pulses, and those get read through the line in here, and then this PRA software converts it into sound. I have entire videos on how to do this, by the way. I'm like looking at my own screen on my other laptop, and like it looks blurry. Why for it look blurry? Do you guys see the blurriness, or does it look clear to you? Sorry using you guys as guinea pigs. I plan to make this fun. Oh, there it goes. Maybe it was me. So anyway, these sounds are going into PRA. Now let's go up here and look at PRA for a minute. So this is PRA, this thing right here. We'll just move that out of the way. And as you can see, we're picking up pulses and we're filtering. And basically what I've done is I've clicked action and I've clicked start pulse acquisition. And what that's doing is that's basically drinking in these little sound pulses and trying to figure out which ones are good and which ones are bad. And it's looking statistically to see what looks like a real waveform and what looks like not a real waveform. You want to get about 10,000 pulses. We're at 18,000, so we're probably good. Basically, we're teaching PRA what the sound should look like. And if you have a check source that you're using to calibrate with, slap that sucker right up against the scintillator at this point, because you don't really want to not have a good amount of a good amount of radiation coming in the detector. You don't want something really weak, so you don't want to like put a soil sample in front and use that to do your calibrate. Calibrate with a check source of some variety, and if you don't have one, use potassium light salt from the store. You know those little cans of light salt? Something like that. That'll work great. You might need a couple of them, but still. Okay, so let's stop acquisition. Stop. And it's going to pop up this thing here, and it's going to say, like, these are all the little mathematical values which tell me the shape, the pulse shape that I think I should be calibrated to. Basically, PRA in a nutshell is saying, look, these are all the values that I think are correct for detecting the difference between a real valid pulse from the scintillator and garbage. If you happen to have a PhD handy, then you can change these randomly. If you don't, I would just click the OK button. I mean, I don't mean to put it like that, but honestly, I find it easier just to click the OK button at that point. Now, let me take away the sodium-22 sample for a minute, and I'm going to put a cesium-137 sample in. This is a small cesium-137 sample. It's a tenth of a microcurie if you live in the US or anywhere else in the world. It's 3.7 kilobecquerels. That means 3.7 thousand decays per second. And the point behind it is I want to get a good idea of how this is going to look. So let's go down here and open this up. This is your pulse height acquisition window, and what it's saying is I have 0 to however many channels. I think I have 1,001 channels or something like that, and each one of these will rise up based on the energy that goes in it. So if your energy is of a given value, it might rise up right here, start building up as it counts more and more and more of them. But if it's lower energy, it'll be making a peak over here and so on. So let's start this thing and see what we get. Now we should have a nice, look at that. A beautiful cesium-137 spectrum. And look at it. Let's move over here and take a look. Oh, that's perfect. Now see, we'll give it a minute or two to fill out here because we're going to calibrate to this thing. Let's do a couple adjustments just to make it look a little better for us. Let's see, bin size. I think that I want, let's see, I think I want to set this to a higher value. Let's try. apply. Was that right? Yeah, higher value. I think I might want an even higher value than that. Let's go with, oh, what the heck am I typing? 0.2. Let's try that. That should be good. 0.5. Let's try that. And what I'm doing is I'm reducing. Oh, wait, I'm making that too narrow. Let's go back to 1 again. There we go. So now it's not too fine-grained. So what we have here is we have change in energy with the left side over here being low energy and the right side over here being high energy. This peak you see right down the middle, that's the primary photo peak from cesium 137 at 662 keV. Photons of this energy get stuck right here. If they're a little bit more energy, they go past it. If they're a little bit less energy, they go behind it. And then you have this nice curvature here, which goes up to a Compton peak. And that comes from, of course, backscatter. Basically, Compton scatter, backscatter, photons are bouncing off and going all over the place and losing energy along the way. What I'm trying to recall here, I haven't used this particular piece of software in quite a while, is how to widen that out a little bit. And I'm trying to recall how to do that. Pulse rate, where is it? Height, threshold, shape tolerance, blah blah blah. Oh, where are you? Bleh. I can't seem to recall. Maybe it was you right here. Counting rate, no, it wasn't you. Well, we'll leave it right here for now. I think we can zoom in by some means, though. That was what I was trying to do. Zoom, 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 zoom. Well, anyway, so basically put, as you can see right here, let's see if I can expand this a little bit. That is definitely our spectrum. And what will happen is the software will spread itself out as far as it needs to. So if it's detecting higher energies, it'll squeeze everything up and make space for that. And that's probably what it's doing right this moment. Well, anyhow, let's get this thing calibrated correctly. So what I'm going to do is stop. And we're going to go to the settings. And we are going to go to energy calibration. All right, so let's make a few notes here on a few things. We're going to hit the S button to start, move our little line over here to E for end. Is that it? Is it S and D? Ah! That's what happens when you spend too long without using something. Oh no, it's B and E. That's what it is. It's B and E. So B and E. Okay, so that was it. That's it. All right, so let me see if you see this or not. Let me try to help you guys out here. Do you see where my mouse is? Right here? There's a red line. This red line is the channel I'm currently in. And it's the if you look up here, you'll see these numbers go down as it goes to the left. That's because the channel, or bin as they call it, is going down. This is the energy currently assigned to it, which is incorrect. We'll get that fixed in a minute. And this is how many counts it got. So if we go over here and click on the big one, we're up in the thousands of count ranges. Let me switch this over here so I can see if you guys are saying anything. Tom, you using one of Steven's scintillators? Yes, I am using one of his scintillators. Let me just stop for a second and say, I like the Gamma Spectacular. There's a lot to be said for the UCS30. UCS30 is a tough system. It's very kind of just ready to rock and roll right out of the box. You don't have to do anything with it. There's nothing weird, but at the same time, it costs a lot more. And with the PRA software and with the GS 111A, there's a huge amount of functionality built in. For example, I think, and I've never played with it, but I believe there's anti-coincidence built into this thing, which I might be using for my solar spectrometry. There's a lot of neat things you can do with the GS111A, and it doesn't require an external power source because it does, but it draws it from the USB and the laptop, so you can take it with you anywhere. So it's kind of like in between the Polymaster and the UCS30. It's like in between, all of its strengths, none of its weaknesses, that kind of thing. Because here, let me show you. Let me take take the UCS30 and run it here for a second. I've been having some trouble with it on this computer, by the way, too. Watch what happens to the Polymaster when I start a spectrum. So let's do one and see. See, look at that. It died. It does this sometimes. I don't know what's up with this. It's been on this laptop recently, too, and I don't know why. The software, like, just bleh, and coughs up a lung whenever you try to connect it. So, come on now. And we cut it off. We'll cut it back on. Very annoying. It doesn't do this, by the way, with the little Palm Pilot you've probably seen me using before. Come on. Come on. Here I was going to show you guys a spectrum and we crashed. It does this a lot. It's been doing it on this laptop and I don't know why. It's probably something to do with the Bluetooth itself. Oh yeah, the 2x2 sodium iodide is great. And yes, straight out of Compton for sure. I like that, by the way. All right, so let's see if we can connect to the pager, and we'll run a quick spectrum, and then we're gonna do the analysis. But yeah, I'm sitting here sipping coffee, so I make all kinds of nasty sounds. Now it won't even connect. Look at that. I don't know what to tell you. Like poly identify. There it is. I write my book on this laptop too. By the way, the picture in the background you saw with the bug, I made that picture. So like, don't give me any copyright crap, YouTube. I like make all my own pictures and all my own stuff. So I don't even want to hear it. In fact, I'd be playing some awesome like background music, but I don't want to get in copyright. I'm like obsessed with that. Staying away from the copyrights. So there we go. We're back in again. Yay, that was fun. All right, let's start a spectrum and see if it can crash again. If it crashes again, I'm not going to go through messing with it. I don't want to spend like 400 hours working with it. The little Palm Pilot works fine. So let's put the source near the detector and see what it gets. All right, here it goes. I think I'm about 5 or 6 seconds ahead of you guys. Maybe 7. This is kind of weird. And look, nice cesium-137 spectrum starting to form, and it looks the same, doesn't it? Doesn't it look the same? Or more or less. Yeah, you see what I mean? And so while that's forming, we'll go back and we'll look at this and compare the two. And I want you to see that they look pretty close to one another. Now give them a minute to match up. And they're not going to quite match up because the units are slightly sensitive at different rates and different levels. One's a cesium iodide thallium doped, the other's a sodium iodide thallium doped. But you're seeing that they're getting pretty close to one another. All right. Well, anyway, oh, by the way, if you've seen this on Twitter or like Facebook or whatever, feel free to like retweet it or send it out or something so other people can like log on and take a look too. I mean, you don't have to like do that, but if you want to, that's like super cool. So you see the two of them are very similar to one another. The softwares, the difference is, of course, the cost. The GS111A and the equivalent systems like it are much, much, much cheaper. They're not quite as easy to carry around, though. As you can imagine, the Polymaster is easier to carry. But overall, I think if you need extreme portability, the Polymaster is the way to go. If you're okay with like carrying a small laptop or something with you, even a small laptop, like netbook sized, then GS111 or something like that, one of the Gamma Spectaculars, is great. And if you're setting up like a lab, then you want to probably get like a UCS30, but I'd also get a Gamma Spectacular with it. So let's see here. So you see they're pretty close to one another, right? In fact, let's just for fun, let's stop this and let's go to identification and see what it thinks. What does it think that it found? Lo and behold, cesium-137. And it thinks that it found 5 4 to the, so 1, 2, 3, 4. Oh, wow. It's a little off on its analysis of the activity, but I've never found its activity analysis to be that accurate. I'm thinking that it probably needs to be in a certain set of conditions, and I've never found them written in the manual, so I'm sort of like blown away by that. Oh, let's see. Xbox Skate Vids is asking the following question: what the heck am I using? Okay. So let's look and see. First off, glad you asked that question. I'm prepared to answer it. The sensor I'm using for the first part, that would be this thing right here and this thing right here. The sensor I'm using is this guy right here. This is a radiation sensors scintillation detector. This is the unit right here, and it's a sodium iodide crystal with a photomultiplier tube in the back. It's the same basic technology from the 50s. It works like a champ. So that's what we're using for that. And just to go back, Spectrum Techniques. Where is it? No, that's not right. Yes, that's right. Okay, Spectrum Techniques, don't sue me. I'm showing them your stuff. Don't get mad. Get glad. I'm using this guy basically right here. Except I'm not using this part of it. I'm just using this part of it right here. I have this too. I just am not using it today. And Gamma Spectacular. Gamma. Hey, look, my videos pop up when I say Gamma Spectacular. That's funny. All right, so anyway, there. This is the thing I'm using. The product device I'm using, the thingamabobber. Neutron? Wait, hold on. Neutron detectors? He sells neutron detectors now? Holy crap, look at that. $449? Someone's gonna get a neutron. Actually, I already have a neutron detectors. That's okay. God, I'm so terrible. It's pathetic. The second I saw like the thing, what did I do? I went nuts for it. I'm a terrible person. Okay, so the actual voltage driver thing that converts like the voltage from, and this is it right here actually. In fact, let's see if my number's in there. 419. Nope, none of these are my number, but I have one of these guys right here. I have a different one. These guys are all cool. I love these things. That other thing I'm using though, if you were looking at this thing right here, let's go into search mode. This is Polymaster. Yes, stupid thing. Polymaster. Polymaster. Poly. So here's Polymaster, and I'm using personal spectroscopic detector thingy bobbers. 1703 GMB. That's what I'm using right there. There it is. That's the GMB, and it has a gamma detector and it has a neutron detector built into it. So this thing's pretty useful. Where to buy? Yeah, I've been to their labs. These guys are awesome, by the way. I've actually been there. It was kind of funny. I walked in the door and they were like, "Yeah, the sign says you got to use a dosimeter when you walk back in the lab. We've got nuclear sources and stuff." So I like reached over. Look what's on my look what's on my hip. Look what's on my hip. Got a polymaster. And they were like, "Oh, excuse me, sir. We did not realize. Well, walk this way, please." So I like wandered on in. Let's see if anybody's chatted as I'm sitting here like going on and on about like weird, stupid things that happen to me. So I was answering which instruments am I using? I have done that. What is a good Geiger counter for the money? That is a super suggestive term. In fact, there's a lot of good ones. I am a fan. I am a total fanboy of the Inspector series. I like the Inspector series. Um, well, go to geigercounters.com. But the Inspector series, you've seen it probably a million times in my videos beforehand. I love it. The Inspector USB is awesome. I think it's like my favorite Geiger counter, probably my favorite ever. I also like Ludlum, but I use that more for scintillation counters. For the moolah, for the money, there's these things called GMCs, like GMCs. What's M stand for in NATO? Like golf. Motel, it's not motel. Golf Mike Charlie, GMC. There we go, motel. Yes, motel. That is definitely the NATO speak. The GMCs are pretty good too, as I have heard. I have never used one before, but they look pretty good. And they're like $100 too, so that's a good deal. But the inspectors are so much more sensitive. All right, so let's see here. What is good guy here? Oh, really? Yeah, it does make you think. That's why I got into this in the first place. Answer questions. Well, God, I wish people answered my questions when I was younger. I had to figure this stuff out the hard way. So yeah, if I learn information, I want to answer everybody's questions because nobody would ever answer my questions, which is really, really annoying. You see what I mean? Let's see. I am nuclear detectors almost every day because I work in a nuclear plant. Well, there you go. Well, if you work in a nuclear plant, I almost guarantee Xbox Skater vids that you probably have Ludlums sitting around, probably Mod 3s or Mod 12s. Those are extremely common to see in a nuclear plant if you're in the United States, mind you. If you're like in some not United States country, then you could have something completely different. You can easily upgrade the tube in them. Is that the GMCs you're talking about that you can upgrade the tube to the Russian one? Because those Russian SBM 20s are pretty nice. All right, so anyway, getting away from all this for just a second, let's put the Gamma Spectacular, not the Gamma, the Polymaster back right over. In fact, I'm going to put it right twixt me legs. So this is where the important parts are, right? And we'll see what kind of dose rating I get from the important parts. So now let's get back to what we were supposed to be doing. My God, I have like no ability to stand track. So let's select the sample here. I'm going to go over to this peak right here. Now this first peak right here is the 32 keV peak, which comes from X-rays from the cesium-137 when it converts to barium-137M. So let's go to the beginning of it, and we're going to hit the B button for begin. Then we're going to arrow over to the end of it, and we're going to hit the uh, D button, E button for end. Okay, so it's B and then E. Okay. So anyway, this guy right here is Compton Edge, backscatter peak, blah blah blah. Let's see. We're gonna do begin, and then we're going to do end. And hopefully we have this right. The problem is this could be the Compton Edge. This could be the backscatter peak. That would make this the 75 keV X-ray fluorescence peak, and 32 could be hidden. If that's right, then my calibration will be wrong. Now, luckily in this case, I actually know exactly what it should look like, so that's not a problem. But one would need to be very careful if you're going to attempt to actually do an analysis. I'm in Canada. We use CANDO reactors. You can do with CANDO reactors. Really unsure if what we use for detectors. I'm in operations. Let's see. Probably ask the rad guys though. Yeah, you could ask them. You probably use Ludlum though if you're in Canada. I like CANDO reactors. So that's I don't know that I just find that very very funny for whatever reason. Um, but anyhow, so let's now that we know these two areas, let's go and assign energy values. And what you're doing as a computer basically, you're saying, look, this is an XY graph, right? So this is the Y, and that's the X. You remember from school, right? So we're saying that at this value of X going this direction right here, this value, which is, let's say, where is this? At the value of 7, we have a Y value of 304. And at the X value of whatever, 61, we have a value of 15,690. So then what we're doing is making a simple linear equation, right? So change in y with respect to x. Really simple. And you don't even have to know like calculus and math and stuffuses. All right, and based on the education rates in the United States, that's probably a good thing. So let's see what we got here. The mean of this channel. First off, are we already using energy? Go away. Don't use energy calibration. Stupid. All right, now, the mean is, where is it? Okay, so the standard deviation is 0.05. Standard deviation is 0.05. And the mean is, what the hell's the mean? 0.7? No. What the hell's the mean? 0.07. No, no, no. The mean should be like one of these little dudes right here. Where is it? 0.074. Let's try it. 0.074. 744. That's off by 10 times. All right, AM 32K EV. I'm feeling off about this. Someone's so used to using the Spectrum Techniques unit that they don't know what the hell they're doing. That would be me. 62. Let's see. The mean was 0.86. I think that's using its actual original units that it uses. I think it multiplies them out or something weird. And then last but not least, we have the standard deviation, which is 0.25, 0.25. So I'm filling these values in against these little values here, and to get them, I'm selecting the regions of interest. Do you need a license to own radioactive materials? Yes and no. So I don't know about other countries. Only in the United States I am speaking. And I am also speaking, let me remind everybody that I am not a qualified expert whatsoever. I am 100% a lay person, which means I know nothing. But basically, put the US NRC, Nuclear Regulatory Commission, has exempt and non-exempt quantity materials. And an exempt quantity material is where they say, look, it's so barely radioactive that we don't care. So like, what's a good example? Cesium-137. If you have anything less than 370 kilobecquerels of it, they're like, you know what, you can't do anything with it. I mean, if you taped it to your head for like 30 years, your chance of cancer goes up like a little tiny bit. So, yeah, it's pretty harmless. When it's less dangerous than like household, kitchen cleaners and stuff, they're like, okay, you can just kind of mess with this. And the idea they did with that is they wanted people to be able to have like little testing sources and stuff to put in, for like their classrooms and things. And Google. So, spectrum techniques. Let me give you an example of what I mean. By the way, I'm not trying to sell this stuff. I just happen to. You keep asking questions that are like in this area. So like I keep going there. So nobody be all like, oh, why do you keep going to this area and showing all this stuff off? See, look, here's nuclear materials that you don't need a license for. See? And there's like a whole list of them that you can get. So let's look at a couple of them quickly. Laminate disk sources. See these little samples right here? They're harmless pretty much. I mean, I'm not, the amount of radiation they're putting off is negligible at best. I mean, you could probably choke to death on one or something, but you can buy the whole sets of them, and they're complete. Even polonium 210, but you can only buy tiny, 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 tiny amounts that the government allows, and they let you have this stuff. Can I make another microscope video? Yes. Yes, I can. But not this way. Oh, got a cough. Hold on. Okay, I think I hit the mute button successfully. Hopefully I did, or your ears just all blew out like eardrums. I like choked on my coffee. So like you can get this stuff. And it's perfectly valid. It's in a NRC exempt quantity. I actually contacted the NRC and asked them about this. I was like, okay, well, what's safe disposal and everything? And they're basically like, I mean, I'm kind of paraphrasing them here, but they were basically like, we don't care. These exempt quantities, you can't do anything with them. They're less radioactive most of the time than like a commercial, than actually like a residential smoke alarm. So they're not really very, very dangerous. I mean, you could choke to death on one. You could throw one at somebody, I guess, maybe, and like it would hit them in the head and not really hurt very much. But so that's the whole point. But people get all excited. They're like, "Oh my God, you'll have cancer tomorrow." Well, yeah, you probably will get cancer. You have a 1 in 4 chance of getting it anyway. And even if I got cancer tomorrow and I went and told the doctor that I was like touching this stuff, the doctor would probably still be like, yeah, the likelihood is probably like almost zero that this was the cause. Things like smoking and just chemicals in your water and stuff. And in the United States, we have entire like cities now that apparently have like destroyed water and lead coming up and stuff. And people are like worried about radiation. Really? Yeah, it's carcinogenic. Nobody's lying. Well, there are people that say it's not carcinogenic, but it is carcinogenic. I mean, it's well known it's carcinogenic. But I mean, overall, it's like they get so worried about it. But it's kind of like the airplane scenario. Everybody's afraid to fly, but your chance of like dying in an airplane is like really, really, really low. The reason people are do it is because they're that if you do get that one tiny itty bitty chance, then it's like horrific and you're crashing and stuff. Whereas getting in your car is less horrific, but at the same time, the risk is like a bazillion times higher, right? Yeah, bazillion. That's a fully qualified uh, probability, isn't it? So anyway, let's get rid of this. So here's the deal. We now know these. Let's apply them. We're going to fit in a nice linear mode. Apply. Let's go over here. And where's the button we need to hit? Where is the button? Where's the button? Where's the button? Where's the button? Data analysis and acquisition. use energy. Let's see if we get it right. Yeah, it's about right now. See, these are in keV, kilo electron volts, thousands of electron volts. And we see our electron volts are shown right here, and that's about right. Right in the middle, yeah, that's about right. So this should be around 280-ish, 240, 280, somewhere in there. And it's a little, no, sorry, 180, 180. I'm sorry, I had that off. This guy right here should be like 400-ish. Okay, that's correct. And this is 662-ish, pretty close. Okay, so we have a pretty good calibration at this point. You're more at risk walking down the street or driving, blah, blah. Yes, yes. Now everybody's gonna be like, oh yeah, well give me the cited confirmation of those exact, exact, percentages and stuff. I don't have them. Go to Health Physicists Society of America and ask them. That same question's been asked to them like 80 million times, and they answer back every single time. Now, I wouldn't go so far as to agree with them. They would be like, for the most part, if you read what they say, they pretty much make it sound as though radiation is almost completely non-harmful. I mean, they don't say that, but they infer that the harm is very low, would be a better way to put it. I disagree. I think radiation's harm's a little higher. I'm not like a paranoid person, obviously. I mean, look, I'm sitting here doing a sample. How could I be a paranoid person? But at the same time, I'm not like a radiophile who's like, oh, I've got to drench myself in this stuff and cover it, all over my body. Yeah, sounds a little weird, doesn't it? Ah, it's not a good day until you've said something freaky. So, now that we know we have a spectrum and we got the sucker set up, let's pull out the sodium-22 sample and get into sodium-22. You are allowed to have trinitite. No, are you allowed? Yes and no. Everything is always yes and no in subjective happy land. But anyhow, basically it's nuanced. Yes, you're allowed to have it if you got it. How do I say this? It is illegal to go get it there. Like you couldn't go to the Trinity test site and pick it up. It's a national park sort of thing now, and like it's illegal to get it. But whole bunches of it was mined and sold out to everybody as presents and gifts and stuff. Like humongous amounts of it back in like the 50s and stuff after it happened. And as a result, there's piles of it out there you can buy. And honestly, if you did get a sample that wasn't legal, I don't know how you would distinguish it from one that was. But there's huge amounts of samples of it that you can buy. And if you buy it from a reputable dealer on the internet, a reputable dealer on the internet, that almost sounds oxymoronic. But really, there are some. Mineral Research Corporation. United Nuclear, I would say, is probably going to be giving you a reputable source, I guess. You can always go and lay on the beach, and yes, that is correct. There is a place in Brazil that's got enough uranium in the soil to like blow your mind. Everything is radioactive to some point. I wouldn't say everything is radioactive. Most stuff is radioactive to some point. Um, there are many particles that they're unknown to decay. So that doesn't mean they don't decay. It means they're unknown to decay. Like, I'm trying to think of a good one. Like a photon. I can't think of what a photon would decay to or how it would decay. Like by what mode would a photon decay? But there's radioactive, at a dead minimum, there's radioactive material mixed in just about everything. I mean, if you run a background, like here, let me get rid of my samples for a second. All samples gone and put away into their little respective lead pigs to hide. And let me just run the thing here and let's hear the background. So start. And oops. Hmm. Haven't heard anything yet. How tall are you? 3 centimeters. I'm basically almost on the dot, 6 feet tall, plus or minus like a couple centimeters, depending on my spine at any given day. I have brown hair. I have green eyes with a little gold ring inside each one of them. I have a pale, darky skin complexion. Very long brown hair that's curly. And like actually, holy crap, my hair is like down my waist. I'm not my waist, down my back. Yes, down to my waist. It's down to my back pretty much though. Yeah. So interesting question. But I have green eyes, and I like my green eyes. That's why my book character has green eyes, because I like my green eyes. This right here is the background. By the way, if you look at the background, this little peak here is probably from cesium-137. That's like escaping from the lead testing pig thing that I have it like hidden in right this moment. But the rest of this is mostly just background. Here's a lot of background. And the reason you're getting background is because there's radiation and sort of mixed into at least everything. So to a degree, who was it that said it? Phoenix AF is correct. It's not actually correct that everything's radioactive, but it is effectively correct if you understand the difference between the two. Let me just check one thing. My Twitter account. Anybody on my Twitter account? Let's see here. Anybody on my Twitter account? Yep. All right, we got rid of all them. All right, so anyway, let's get back to what we're doing as I make my mock Murica accent. Because Murica. Stars and stripes and eagles and stuff. Okay, so let's stop that. Now let's put in the sodium-22 and get to the frickin' point. My God, I don't stay on point whatsoever, do I? Now we're going to be putting in 37 kilobecquerels of cesium. I'm so used to saying cesium of sodium-22. Now let me do some quickie math. All right, Wolfram. All right, so let's do some math right here. Wolfram alpha. Let's see here. So 37. Let's see here. KBQ, 37 kilobecquerels. And we're going to multiply that by E, Euler's number. Some people mistakenly call it Euler's number. Raised to the negative power of natural logarithm of 2 divided by the half-life. That's an ln, right? Yeah. Which is about 2.6 years, and then multiplied by the period of time that's gone by. Now, this sample is from March of 2013, so hold on for 1 second here. And let me just calculate how long it's been from March of whatever until now. So March 2013 until now, and then we'll get that in days and years and stuff. That's 3.5 years. So 3.5 years. This won't be exact, but it'll be kind of close. And this will tell us approximately the activity. So approximately 14.55 kilobecquerels remain. To put that into perspective, and percentage-wise of the original amount, we're at 39% of what was originally in the sample, plus or minus. I mean, you saw that I didn't do that out to seconds and stuff like that, so it's not the absolute most accurate thing ever. I love this. Series representation for when you want people to think you know a lot about math. Just copy this on your board at work. People will walk by and think that you're a genius. Because, like, God, look at that. What evil person writes that? What evil pure mathematician writes that? Oh, God, just write this little dot right here by the 40. It looks better. Okay, so anyway, we'll take the sample. Let's stick it inside the spectrometer. And I have a, just to let you guys know if you do anything about this, I have a couple pounds of lead gathered around this thing. And I have a piece of copper in between the actual source and the detector itself. And the reason I did that is because I wanted to cut down on some of the x-rays that will come off of the source. Okay, are we ready? Are we ready, friends? Excellent. Okay, so I'm going to start this and let's see what it looks like. Let's start this up. Boom. There it goes. I swear that I don't hear anything coming back. Do you guys hear the sound from my machine like earlier? It was making that weird sound. You know, the... Do you hear that? Okay, I hear it now. I had my volume down because I'm dumb. Let's see if I get anybody saying, yes, we hear it. Oh, wow, this got caught up. I didn't hear anything. How tall are you? You can always lay on the beach in whatever Brazil. Yes, I can. Let's see. I would love to stay here. How's the stream going so far? Anything interesting happening? Stream? No, it's going pretty well so far. Let's see here. Moving right along. positron emitter? Yes, it is. And let me get into that in just a second. You are good at math. Yep, 1 plus 1 is 2. And the derivative is 0. What would you recommend as your first Geiger counter under 100? But why does everybody always want $100? Like, it's really hard. Really. Senpai, notice me. Height. Basically, I would go with the GMC. That's Golf Mike Charlie. GMC, like a 100 or something on Amazon. That's about the best you're going to do for $100 that I know of. Now, I may be wrong. There may be better ones. That's the best I know of. Do a British accent. Okay, I'll do a British accent, but you understand that I'm not British. Like, I mean, ancestrally, I'm like, Scottish and stuff, but I'm not really British. So that means my British accent is going to be the most horrid thing you've ever heard in your life. So I'm going to be all like, your British accent's terrible. Yes, of course it's terrible, because America. I'm getting such a kick out of the whole America thing, by the way, too. By the way, I'm not, like, actually one of those America people. I just like saying it because it's funny, because I have Tourette's, so I repeat things over and over and over and over and over and over. I do declare that every person who starts with a British accent must start with the term I do declare, which is required, if not slightly redundant. Yes, as you can see right here, we're at 330, nearly 340,000 counts and rising slowly. And the detector, wait a minute, that's moving really fast, it's hard to tell. My accent is horrible, even though I've been to Britain many times, and British people now hate me. I am the enemy of all British people, because my accent is so terrible. Yeah. Sean Connery could do an accent. I could do a Sean Connery accent. Sean Connery is going to teach you about nuclear physics. Alright, so anyhow, let's see here. It sounds like when you had a... Senpai noticed me. I just like that. That's funny. I watch so much anime, like, so it's terrible. I, like, see that. Yeah, let's see here. DIY Geiger counters kit. Yeah, I've seen those before. Those aren't too bad. Alrighty. You sound like Bane. We will teach you what you need to know about gamma spectroscopy, and then you will achieve the best that you can. Yeah, Bane. Okay, great. So I can be Bane now. Anyway, what you're hearing in the background, that sound, is a combination of all of the gamma energies being converted to sound. Low energy sounds make low sounds. High energy make high sounds. B? B. So, basically put, this is the spectrum for... Shut up. This is the spectrum right here for sodium-22. Now let's talk about sodium-22. Let's work on our sodium-22 awareness. It has a half-life of about 2.6 years-ish. So that means every 2.6 years, more or less, half of it goes away. That's why you notice that my sample was lower in activity than it was when I bought it. To give you an idea what its specific activity is, you merely inherited it. I was born with it. B? Born with what? The specific activity is the amount of radiation you would get from a single gram of said substance. In this case, if you had a gram, of sodium-22, you'd be experiencing about 231.22 terabecquerels per gram. Terabecquerels of activity. I mean, that's a humongous... That's 231, what is that, trillion decays per second. This is just an absurd amount of radiation. We'd all be dead and stuff if I had like a gram. That's why you can't have a gram. It's like a ridiculous amount. Let's see here. It's decaying to neon-22, and it does this for the most part via beta-positive emission, but it also does it, that's just normal beta-positive decay, but it also actually undergoes electron capture as well. And in the beta-positive, what's happening is the protons and the neutrons, there's energy holding them kind of together, the strong nuclear force, and this binding energy, there's sometimes excess binding energy in between the protons and neutrons. You have like these little particles called gluons that are bouncing back and forth. And there's certain situations where this neon-22 is going to be less, it's going to take less energy to be neon 22 than to be sodium 22. So the proton, one of the protons, is going to use some of that surplus energy that's holding everything together, suck in a little bit of that, and it's going to rise itself up to being a neutron. Neutrons are heavier than protons. It does this through quark flipping, like a quark's going to flip. So a proton is two ups and a down, and a neutron is two downs and an up. So basically, what it boils down to is an up quark will flip to a down quark, and to do that, it's got to gain some energy. Wait, isn't that a noble gas? Yes, it is a proud and noble gas. So basically, neon it is a noble gas. But the little tiny sample container I have, we're talking about this is on the scale of like atoms and stuff at this point. Like, so nobody's gonna know. It's not like gonna like blast gas out all over the place and blast gas. So basically, what happens is a proton turns to a neutron, and it does that by gaining extra energy that it needs for this transition from the surplus of energy of the other nucleons that are going around in the nucleus itself. They're all holding each other together, and it kind of sucks in a little bit of that energy. Yes, no blasted gas. So it does this. There are certain situations where electron capture occurs. What happens is one of the really low electron shells, if you like, the K shell specifically, it has a like electron that's kind of flowing by there, and it gets like a little bit too close to the nucleus. The nucleus is like snatch, and it grabs a hold of the electron and drinks it in. And the energy that it takes from that is enough to allow a proton to switch again to a neutron. It's the same basic decay. It's just where does the energy come from? And in both of these two situations, most of the time you result in a 1274.5 keV gamma. So we should find that right here is about where we want. Now we only did a simple linear calibration, so this might be off a little bit, but that right there should be 12. And it's not exactly. It should be 1274, but as you can see, it's like 1200 and something. 1274 is right here. So it's not off by much, just a little bit. We're not doing like a terrible job here, but the calibration's drifting a little bit, and as we go that way, we get worse and worse and worse. And that means that this guy right here should be around 511. And we see that it's pretty close to 511. Now you're saying, where's the 511 come from? Okay, so Tom, look. We know that right there is coming from the decay. So the atom decays from sodium 22 to neon 22, and it's an extremely highly energetic state. It's got to let loose that extra energy, and there's the extra energy right there. Where does the 511 come from? Because the decay doesn't cause the 511 at all. Well, that's the neat part. That's the antimatter part. Geordie LaForge, how is the nuclear? How is the antimatter working? Well, it's working great, Captain. So basically, put antimatter is how it works. You have a positron that emits, which is a antimatter electron. It's an anti-electron, but it was invented. It was discovered long ago, so they gave it like a name. They used to name stuff. Now they would just call it like an anti-electron. But back then it got a name, and it was called a positron, an opposite of an electron. So positrons are flying around in the air, and what happens is the positrons almost immediately, they have a positive electrical charge of 1, almost immediately encounter electrons someplace in the air, which has a negative electrical charge of 1. And the two start spinning around each other really, really fast. They go round and around and around and around and around each other, forming a sort of matter that's called positronium. So like you can't make it into a block of metal or anything like that. Positronium wouldn't work, because it's kept in its own little perfect confine with the positive and negative, near one another. I don't even know if you could form a covalent bond somehow with one. It wouldn't last long enough anyway. So as the two spin around one another, eventually they encounter one another and they annihilate, blasting all kinds of energy all over the place. They shoot out two gamma rays. One gamma ray goes one direction, and the other one goes the exact opposite direction, and they both have 511,000 electron volts, 511 keV of energy each. So each one of them blasts out and goes a different direction, and that's the rest mass of an electron. Ironically, makes kind of sense. So anyway, that's what happens, and that's where this peak's coming from, right here. So what do we have? We have right here the actual decay energy, and right here we have the actual annihilation peak from antimatter. That's from antimatter. Stop and think about it for a minute. Stop and think about it. That's from antimatter. Antimatter. If that doesn't amaze you, then I can't amaze you, because that's freaking antimatter. Like when the Enterprise blows up, which it does like every 3 or 4 times a week, That's how it's happening. Now, here's the difference. We have single atoms, dozens of little atoms making antimatter. Can't you also say MeV? Sure, why not? Yes, you could. So instead of 511,000 electron volts, it's 511 kilo electron volts, and it's also it should be mega electron volts. It should be 5.11 mega electron volts. So it's just 1,000 by 1,000 by 1,000. Have a good night, all. Oh, okay. Well, good night then, a dude man. So yeah, make sure I keep up with everybody's like things and stuff. Let's see here. Two more notifications on my Twitter feed. People, yeah, people responding to my kitty comment. Have a good night. Yes. So, very good night to you as well too, and thank you to everybody so far who's joining me. By the way, I'm not about to end or anything. I'm just saying thank you. So I don't want everybody to be like, oh, I guess he said thank you. I guess we're all leaving now. And by the way, let's look and see what my background radiation looks like now that I got this big old source out right here, and it's still the same amount it's been before. See, not much at all. If we put the detector closer, it'll go up. See, I put it closer, it goes up, but I pull it away, it goes back down again. So anyhow, um, basically put we're producing antimatter, and we know we're producing antimatter because we see this. That, friends, is antimatter. That is an antimatter peak right there. That was made by antimatter, no joke. And if we're having antimatter and we're matter in the regular matter is connecting with it, and the two are annihilating each other and producing energy that we are then using for some purpose. In this case, we're converting energy to sound. Is it not accurate to say, on the most technical of details, that we actually have an antimatter reactor? Am I wrong to say that? I don't care if I'm wrong. It sounds cool. Heck with anybody who doesn't like it. The rest of these things can be explained too. That right there is a Compton edge, and this dude right here at 200, that's a Compton peak, that's a Compton edge, and that's a backscatter peak probably for this guy right here, and so on and so forth. So let's get rid of these two. And I'm not going to make a pretty picture out of this one because I find that using the UCS 30 makes the nicer looking pictures. Where is it safe to store radioactive materials? Well, not in a shoebox and not under your bed, that's for sure. I usually recommend using something called a lead pig. Lead pig. So, let's look at lead pigs. Lead pig. God help me. All right, so here we go. That right there. In fact, that's actually one that I own. I own this particular lead pig right here. So what you do is you put them in here. Now, a couple things to understand about this first. And then I will get to the next question I just saw in a second too. Basically put, you don't always want to use lead for storing nuclear materials. That's not actually correct. So if you have beta radiation and stuff like that, like what I'm dealing with right here, yeah, sure, drop them in one of these. If you have an alpha emitter, you want to probably stick it in something that's maybe plastic, because the alphas would strike the lead and cause X-rays. In fact, the electrons will do it too, in the positrons, but the X-rays won't be strong enough probably to make it out. But if you have a strong alpha emitter, which for the record you shouldn't have a strong alpha emitter, the only pure alpha emitter legally available is polonium 210, and you can only have like a little tiny microscopic rounding error of it. But if you just so happen to have one, you'd want to put it in something like plastic, or else you're going to get X-rays all over the freaking place. It is incorrect to think that lead is just always the perfect thing. Now, if you have these little dorky check sources, we're not talking about real sources here. We're talking about these little dorky check sources. They're not going to hurt you. What a stupid thing this is. Pardon me as I go on a rant now. Do you want to change the color scheme to improve performance? Blah, 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 blah. Annoying suggestion, annoying suggestion. No, you fool. What do you think I do for a living? Shut up. I know how to fix things. Why would it ask me that? Grumbles, etc., etc. I get excited. So anyway, lead is usually pretty useful for those little dorky ones, like the ones that these little samples that you guys are using. Lead pig. That's funny. I don't know about some of the rest of this stuff, and I bet you it's going to go downhill if I keep going. This is the internet, so Within a few seconds, if I scroll down further, eventually porn will somehow appear. How do I know? Because there's nothing you can type into Google that doesn't result in porn. Well known fact. Anyway, just remember to store your alpha sources and no, niet. Do not store. Do not do. Never, ever put an alpha source in your beryllium because you will have neutrons coming out the wazoo. Neutrons that will make a neutron soup. You will barbecue yourself in neutrons. Uh, Yes, it's pretty much like a X-ray. Yeah, don't do it. So if you stick a nuclear source on lead, you produce 75 to 85 kilo electron volt X-rays. So anyway, I say wrap them in plastic, shove them inside the lead pig unless they're alphas, in which case you should question why you have an alpha source that strong. But if put it in a box. If you have a strong uranium source, something like that, that does put off legitimate alphas, that is like perfectly legal because you can own uranium all day. There's nothing wrong. I'm talking about natural uranium, by the way. I usually suggest taking natural uranium and sticking it inside like a little cardboard box and then putting it behind a couple center blocks and always keep it away from where you sleep. Like, don't put it in your room. I mean, why would you do that? Put it in like a garage or something. If you're really paranoid, dig a hole in the backyard and shove it in a plastic bag and stick it in there. Watch out for dogs digging it up. Most of these check sources are very weak. Just to remind you guys, in case you're not aware of this, you have smoke detectors in your house, right? Right? Smoke detectors, nod with me. If you have smoke detectors, they have what is it? Nearly 370 kilobecquerels, as strong as the sodium source I have right here of radiation. I mean, of americium-241 in them. They're emitting it all over the place. You're getting bombarded with X-rays all the time. People are like, "Oh, I can't believe you're holding this X-ray source or this gamma ray source. You're going to be dead in a week." Well, what do you think the smoke alarm over top of your head is, dude? What do you think that is? It's the same activity. It's the same amount. Same. And people freak out and they're like, "Oh my god," and they didn't even know that. What do you think the americium is, friends? What do you think it is? It's turning into Neptunium-237 right over top of your freaking head, and nobody even thinks. Do not do that. I would just give you an advisement about smoke detectors. Never rip one apart. The reason is because they contain americium-241 and neptunium-237. And, well, no, not, they have, hold on. They have weak X-rays, yes, but they also have pretty strong gamma rays that come off of them too. So, yeah. But anyway, so basically what the hell was I? Yeah, don't take them apart because the americium-241 can get out and can get on you, and that can be dangerous. You don't want an alpha emitter inside of your body. Like, you don't want that. Let's see here. All right, so anti-proton.com, AM241. Let's look and see what I think about this. Here we go. Look at that. Pico Dream Hamsters? Oh, come on now. What's with that? Stop that stuff. Stop taking my images. It's not even on Pico. Wait, that came from me. Search by image. All right. Okay. Where is my copy of americium-241? How am I supposed to look at americium-241? AM241. All right, give me a second. Okay, there it is. Like, why is that not where it's supposed to be? So give me a second and I'll put it on, move it from one computer to the other. Okay, here, there. And also, how about the sound effects from it? There. Okay, so there. Now, hopefully you guys can see this. I don't know why that was just such a pain a second ago. Let me get back to my to the thing here so I can see what you guys see. You should do this more often. Just drink some vodka. Yeah, why not? I was thinking about doing it a bunch. This seems fun. And then just upload the video afterwards. Now look at this americium-247 spectrum for a second. This is a 6-hour test of a residential smoke alarm I bought for like $6 at Target. Oh my god. Look at it. Look at these. These are solid freaking gamma rays right here. And some X-rays. A lot of X-rays. Whoever said X-rays a second ago, somebody said X-rays a second ago. They were correct, but there's also some solid stuff in here too. And look at it all. This is the spectrum of what's hitting you. So like you are getting hit by stuff when you have a smoke detector, and they have them all in your house. I mean, if you have 6 or 7 smoke detectors in your house, then you have more radiation in your house than I do in mine, just for the record. So I mean, it's not dangerous really. I mean, and think of the danger of you not having this. What if you had a fire and you died because you didn't have a smoke detector? My point isn't to scare you away from smoke detectors. It's just to say, like, before you get all like, oh, you'll be dead in a minute from cancer. Really? Are you sure? So anyway, let's get back to this for a second. So what do we have here? We have the decay energy, and let's look it up in the internet and see if this matches up, right? So sodium 22 decay scheme, and look at all these decay schemes, and what do they all show? Sodium 22 decays to down via beta positive or electron capture, and then it emits a 1274.5 keV gamma. What do we see? Pretty close in the energy right here. We're off in our calibration a little, but that's approximately, it's 1206 here. It's pretty close. This right here looks like the primary gamma that we expect to see. The other thing you expect to see from the sodium 22 is right here, the 511 keV spectrum. Sodium 22 gamma spectrum. Spectrum. Spell that right. Any of these mine? No, of course not. Mine aren't cool enough to be up here. And look, you see right here, um, you see them right here. You see all the little peaks exactly as you should expect. These look, oh God, that's from a nice detector right there. These look like mine for the most part. That right there is the 511. That right there is the gamma ray, and there it is. So this is the spectrum exactly as you would expect. Alphas are small distance travelers. That's correct. Technically, alphas are like 5 or 10% of what hits us from space. By the way, from the sun, so they can travel all the way from the sun to here. But the thing is, they're coming through space. That's why. That's a vacuum. The reason alphas don't make it very far is because they hit stuff along the way. They have a +2 electrical charge, so they're very attracted to things. And as they move past pulling and tugging electrically at stuff, they lose energy and they slow down, and eventually they just kind of run out of go juice and they just kind of stop. So that's how alphas come to a stop. And then an alpha particle will pick up a couple of electrons, 2 specifically, and it becomes nothing more than helium-4, like you'd put in a little party balloon. That's it. Isn't that creepy? So when a smoke detector comes in between alpha and smoke, yeah, that's one of the methods they use. I think they're using the technique of cutting down on the actual charge that you get moving. It's a ionization detector inside of the smoke detector. I get 3.05 microsieverts contact. Yeah, I don't doubt that you do. They do put off radiation. Um, Looking to see some of these other little things that are in here. Why is americium 241 in the smoke detector? Because it emits alpha. The alpha radiation is used to basically you have a think of it like this: you have a radiation detector that's detecting the radiation. The second something comes in between, it stops, and so that's something that you see coming in between is the smoke. It's kind of like blocking it, and so they have what are called photonic smoke detectors. Basically, it's just a little laser or light LED or something like that, and when smoke gets in between, it blocks the light, and that works exactly the same way. So it's the same basic technique either way. And so that's how we do that. Now, if you guys want, I'll quickly set up the what is it, the Spectrum Techniques detector. That would take me like 2 seconds to do that. So Spectrum Techniques, let me download it. Support software downloads, and we'll see what it looks like, because you guys might get a kick out of that too. UCS 30, that's a 32-bit. Where's 64? UCS 30 64-bit. Maybe. Go to Russia. They use plutonium, and yeah, they do use plutonium. Amazingly enough, You can, well, the alphas themselves will get blocked by the gas mask, but what you're really looking for is whether or not the alpha emitting material, that which is emitting the alpha particles, gets blocked. And that you can block if the smoke detector blocks that chemical, it works. So, like cesium-137, for example, which is not an alpha emitter, it's a beta emitter, but cesium-137 behaves like cesium because it is cesium. So, whatever you would use to block the chemical cesium could be used to block the chemical cesium-137. So, you see what I mean? It's just a slightly different number of protons and neutrons. Do you know the penetrating power of, not off the top of my head, but muons are pretty dense. They are not dense, but they're heavy. They have a tendency to slow down pretty quickly in our atmosphere and attenuate, and they spall. They break apart, if you like, producing smaller particles, lighter particles, and that's called spallation, which makes a localized particle shower. So you get like a little, like a shotgun blast of particles, which I pick up with my detector. That's kind of one of the ideas how it's supposed to work. So anyway, let me just hook up the UCS30 and show you guys what that looks like. Since, I mean, we still have some time here. I mean, there's no real time, but I mean, people seem to still be like, interested to some degree. So let me just hook the sucker up. I'm doing it right now as we talk. So let's see here. I'm going to cut off the GS111. Let's cut that off. Next. 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 All right, so we get rid of that. We're going to unplug this and pull all of its little cords off. What is the highest amount? Okay, yeah, I forgot all about that question. The highest amount I've ever that's a toughie. Probably technetium 99 from a patient at a heart clinic. I've had a couple family members and stuff that have got nuclear stress tests. Technetium 99 is hot like you would not believe. That will seriously toast you. It won't hurt you. Microsoft Visual Studio, probably something like that. Already exists. No, don't overwrite anything. Probably not want to do that. All right, so that's probably it. I've also been around some reasonably potent uranium samples before. That's probably the hottest I've ever been around. Some of those can be, like on my inspector, I get over 1,000,000 counts per minute if I'm near somebody with a fresh technetium 99 source in them. And I don't remember how many microsieverts per hour it is, but it's a pile when that happens. Device driver wizard. Now don't need a reboot, okay? No reboots. Don't even ask me for a reboot. I don't even want to think about a reboot. Reboots are stupid. We shouldn't have to reboot all the time. Let's see here. Radioisotope thermoelectric generator, not a nuclear generator. Yeah. That would definitely be hot if you had one of those. Oh my God, would that be hot? I would recommend not going near one of those unless you actually know like what you're doing. I do not know enough about what I'm doing to go near one. I will not be ever going near anything like that for obvious reasons. We'll just steal the power adapter off of my laptop. All right, it doesn't need it. And we will take this and move this over here. And then we will plug... no, I can't plug that in. That one won't work. I need a power adapter. Give me 1 second to get a power adapter. More than you could imagine. UCS 30 plus the detector, 4,000 plus. Polymaster 1703 GMB, 3,000 plus. Gamma Spectacular GS111A itself is about $300. Detector to go with it's another $400, $500, $600, depending on what you get. Yeah. Give me like 2 seconds to grab a power adapter. I'll be right back. Alright, here it is. Here we go. Power adapter. I had to hightail it all the way downstairs to grab one. Alright. Yeah, it's expensive. It is not a cheap hobby. If you think it is a cheap hobby, it is because You are wrong. It is not a cheap hobby. Okay, we're plugged in. UCS30 is plugged in. It is powered on. Installing device drivers. Okay. Hi, I'm the devil. Okay, hey devil. Message retracted. Huh. Wonder why. If I were given a PU-239, I'm going to keep it? No. No, I would immediately report it, immediately get rid of it, and would have nothing to do with it whatsoever. Nothing whatsoever. I have nothing but perfectly legal exempt quantity samples that you can get at a science store. That's it. If I encountered something like that, okay, we're not going there. So anyway, yeah, let's go ahead and see if this thing's ready to go. And I'll show you how this works when you use, there it goes, when you use the, can you guys hear me by the way? Okay, good. If it were legal to own it, if it were actually legal to have a sample of that, then yes, I would own it if it were legal. I'm not afraid of it. I don't think it's terribly dangerous. I'm talking like a microscopic sample, but only if it were legal. Yeah, I think so. I have a cobalt 60 sample, but it's again, it's a very tiny amount. All right, so let me go ahead and get this going. Let me put the sample up against the detector, and let me show you what the UCS30 does. Now, the UCS30 costs a little tiny bit more, and you get a couple extra little candy treats along with it. So let's go. Where is it? Did that not start up? Oh, there's the cat. All right, you need to leave. Okay. Whew. The cat attacked. All right, so Okay, think it's working better now. You should be able to hear me. Okay, my guess is that when I plugged in the USB device, what happened was the USB chain reordered itself, and most likely this the software here like lost its probably lost its reference. I don't know how it does it in the back end, and I don't usually code for USB. I haven't done that in years. So anyway, let's make sure this thing works. Let's set our spectrometer up here. Did you take that pic, Tom? Yes, I took the picture. Basically, I took that with my camera. Put it on Twitter actually yesterday. So it was extremely crazy that the little bug just landed right in front of me. So I like photographed the hell out of it. So let's go up here and take a look at this thing and see what we can do. So we're going to go to settings and we're going to go to high voltage and get this thing set up. So we're going to set the voltage for our detector at 850 volts. All right, positive. We're going to set our conversion gain, so how many of these little dudes we have here, how many little channels at 1024. Positive, we're going to just leave everything the way it is, and kind of lower that number down there as low as it'll take, and click OK. And now we are on, no, we are off. Now we are on at high voltage. Let's run the detector and see if we get anything. Just to see initially, linear. Are we picking up anything? Yes, but not much. Let's see here. Let's put this up against this and see what we get. Oh, okay. That's the problem. We are way too high. Let's lower ourselves down to about here. Okay. Now we're right. Now we could set ourselves up that way if we want to, but let's use the automatic device. Watch this. Settings, energy calibration, auto calibrate. Now this right here is what the money's for, in case you're curious. What's going to happen is this machine is going to actually auto calibrate itself. You'll need a cesium-137 source specifically. You should use at least 37 kilobecquerels. I have 3.7, so this isn't very much. So this could take like an extra minute longer than it normally does. But you can see it's definitely working. It's definitely doing its thing. See it going? And what it's doing is it's increasing and stepping up that voltage until it gets it right, and it's actually going to calibrate itself, energy and everything automatically. You can go get coffee while this is happening. If I had a stronger source than I have right this second, then it would automatically have occurred. I actually have a stronger, I have a couple, but I didn't bring one in the room because I didn't want it to contaminate the test I was doing. So look at it go. Look how fast it goes. So when you shell out a couple extra bucks, you end up with this. You're trading convenience for like cash. Overall, I wish I had saved my cash and gone with the GS 1100 from Gamma Spectacular. And by the way, that's nothing to say negative whatsoever about this Spectrum Techniques unit. It's awesome. It's just like I realize now I could have spent a lot less and I would have had to work harder. But I could still have gotten something good out of it. Does that make sense? So, uh, yeah, look at it go. Oh, see you later. And it's in the fine calibration now, and soon we'll have that done. And we'll let this run for seconds to see that we have a good solid calibration. Let's go to pixel size 3. This is the one that I've done the most work in. That's why I'm like far better at using it. Oh, have fun with nuclear physics. A real quick off topic. Continuing situation. I haven't really paid attention. I like got so absurdly in depth with Fukushima when it happened that like I sort of burned out on it. Like I mean, not to say like I don't care. It's not like it's gone away. It's surely there. It's still a major problem, in fact. But like I don't know. I've spent too much time working on it and like lost my marbles. What time is it in America? Well, America's a slightly big country. There's a couple times in America. My current time is 9:27 p.m. I'm in the East Coast, but it could be 6, 7, 8, 7:27 on the West Coast. America, and that's Florida scuba light. Well, yeah. If you're in Florida, you're definitely in the East Coast. Uh, so yeah, it's like 9 o'clock ish or something like that. Look at that. Look at that Cesium 137 spectrum. Isn't that nice? And you see what you can do with this, guys. You can stop it. You can smooth the data. And look at that. See how nice that is? So that's Cesium 137. That's the Compton Edge. That's the backscatter peak. This whole thing is the Compton Plateau. This is the This is the 32 keV X-ray peak, and that right there is the X-ray emissions, the X-ray fluorescence peak. All right, mute, lab assistant, mute. You must leave the room. Go. His goal is to step on power cords, anything possible to shut off the laptops or cause a disaster. His goal is nothing short of destruction. Uh, I'm from India. Well, actually, you might find this interesting. My third Ember book will take place partially somewhere in between India and Pakistan. You know where the Indus River is. So it's kind of like a give or take as to whether you're in India or not. But it will actually occur in that place. I'm sure you've heard of the ancient civilizations that existed in that area. They're ever so slightly popular. And I will be dealing with those. So I've been learning a lot about India recently. I thought it was kind of interesting to learn a lot about Hinduism, actually. By the way, I'm not a Hindu. In fact, I'm not particularly religious. But the stories are neat nonetheless. I always get a kick out of religious stories, even though I'm not big into religion. The stories are neat. Um, would you say that the fish from the Pacific are not safe to eat? No, I eat them all the time. They're tested by the FDA. Uh, Now, the FDA is not the greatest thing out there. I don't think the FDA, is always perfect and 100% wonderful and everything, but they have large detectors for looking for overt radiation. I'm not talking about like trace radiation. I'm talking about like overt. The idea of like a Pacific fish that swims by and like drinks up a bunch of the stuff and then flies over here. Nitrogen 16? Oh, N16, that's usually used. N16, by the way, is usually used to determine the initial coolant leaks in reactors. Maybe. It puts off a really, really high energy gamma if memory serves. So I probably could, as long as the gamma doesn't exceed about 3 or 4 MeV, because that's pretty much my upper threshold. And it would have to be a potent amount. The only reason you'd be looking for N16 is if you were looking for a coolant leak in a reactor. But yeah, I wouldn't say that they're unsafe to eat in general. I've been to Japan. I've been on the West Coast extensively. I've tested. I've never found much of anything. In Japan, I found a cesium-137 reading in the ground in southern Japan, but I was also near Hiroshima. And you can take a guess why it's possible one might detect that in Hiroshima. So I was never able to confirm that. Don't listen to. Well, yeah, they're probably not going to test very high because cesium-137 is going to form cesium hydroxide and float to the bottom. You're not going to get a lot of radiation unless you're really close to the area. Like I wouldn't eat oysters, for example, from the area. It depends on what you're eating. The act of just putting radiation into the ocean, radioactive material in the ocean, doesn't mean like everything's destroyed. And those videos you see with like the animals that have like lesions and stuff, the reason that doesn't add up is because in the ocean where the water and everything, it's all there's like a huge amount of if you were looking for that would be. Oh, I'll get to that in a second. If you're looking at those animal pictures, you have to kind of ask yourself this interesting question: how come these animals that are living in this humongous Pacific Ocean, where you can test the water and get almost nothing off of it, how come they're getting these huge lesions that people are ascribing to Fukushima without proof? Yet you can go to Chernobyl, where you were literally bathed in radiation that is 100%. We know it's coming from the reactor. I mean, it's not like there's any question as to whether or not Chernobyl's from the reactor, and the animals are happily living there. Oh, don't get me wrong; they probably have cancer rates and stuff that are far above what they should be, and other diseases and things like, for example, various forms of anemia and things like that. But you don't see the stuff they show you. What they show you in these pictures, these doomsayer pictures, they show these bloody lesions and all these messed up things and plants that are growing all over the place. You don't see that in Chernobyl, where we know there's vast amounts of radiation. You can go there right now with a detector and it goes bananas all over the place. So One must ask how that adds up. Well, if you go look in the books, you'll see that plant mutations have been studied for years. They've existed long before humans ever came up with nuclear energy. And as for the lesions, why would you have those big lesions anyway? I mean, the only way you'd get something like that would be acute radiation poisoning. I mean, the thing would have to like swim right through the exhaust waters right by the plant to get that kind of a dose. Long before you, even after you get enough radiation to make your cancer rate actually go up, like a good amount, you still aren't going to notice lesions. You don't notice. That's one of the dangers of radiation is you don't actually notice the physiological effect until it's already close to like deadly levels. So like you wouldn't notice that unless you were at extreme high levels, even if it weren't safe, even if you were already in cancer levels, you wouldn't be seeing any of this kind of stuff. Like Tom is flying to Chernobyl. No, 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 not flying to Chernobyl. I don't want to go to Chernobyl. I actually have no interest in going there. I don't really want to be around dose levels that high, mostly from the dust and stuff. I'm not really worried about standing around it. I would just be in like a Class B hazmat suit the whole time. But my point is that you see these fearmonger things, and the problem I have with that is this. This is what really bothers me about this. There are valid things out there. For example, the real reactors that really are still melted down partially, and lead in people's soil, and all kinds of other stuff that's valid problems. And when people hype up problems that aren't there, and they're detracting from the real dangers. So instead of spending our time and money, like take chemtrails for example, there are no chemtrails. Is yes, scientists have released chemicals in the air before. That has been proven. I mean, NASA even came out and said, "Yeah, we're doing this," and they actually said it, and then they did it. It wasn't like conspiracy; they did it. But when you spend time and resources, imagine all the websites and the money that goes into looking for chemtrails. Imagine if you instead put that on like working on curing cancer or actually going towards real problems that actually exist. I mean, it's people's money. They can do whatever they want. First Amendment, they can spend all day long filling websites up with this stuff. But all they do is they put out so much fake information that nobody knows what's real anymore. If without empirical analysis, people don't even know what's real anymore. You wouldn't believe how much fake data there is out there. And the conspiracy sites just pump more and more fake data out there, and to the point where they have so much of it out there, they can start citing one another and being like, oh, these other 12 sites all say the same thing. Look at our citations. And then you find out they're all just saying the same garbage. Like, for example, radiation in the rain post Fukushima drove me nuts. I would go out there all the time testing with my equipment, and I never found cesium 137 except in a rainwater collection bucket and barely a trace of it, which took 6 months to make. And even then, there was no way to actually say whether it came from Fukushima or Chernobyl or any of the other dozen possible sources. It was obviously man-made, but I mean, which one we don't know. And these people had people so afraid they would contact me with emails. People terrified because they could detect it in their car, the radon washout. These people are terrified. And they're needlessly terrified because people have scared them to get ratings and stuff, either to get ratings or because they were just misinformed themselves. And it's very annoying. It's very, very troubling because these are real, actual issues that need to be looked at. Yeah, yeah, and all the nuclear bomb tests. I mean, there's been like 1,000 nuclear weapon detonations on Earth. I mean, that's what kills me. People were worried about a meltdown. There's been 1,000 nuclear detonations. Hundreds of them were big mushroom clouds into the air. Vast amounts of material. Nobody mentions that. But they're like, oh, look, a reactor meltdown. I'm not trying to downplay it. There was a tremendous amount of radiation release. But to suggest like the one of them is a problem and you don't even mention the other one, it just kills me. It drives me nuts. What do you think about? Let's see. What do you think of several nuclear bombs that have? I think that's bad that they're there. You can't do much with them now. They're not probably usable anymore. The cores, the Pu-239 slowly builds up other byproducts like americium-241, for example, and other sorts of things, and makes them less and less and less effective. I'm not worried about a bad guy country getting them or anything like that because most of bad guys that would do anything bad don't have the technology to get to them. The countries that have the technology to get down there and find them already can make the things anyways. They wouldn't want to like these hand-me-down rejects from the olden days would be very useless to them. So that's why I'm not too worried about them down there. I don't think they'll go off. The explosive lenses on them are probably pretty much inert by this point. I mean, there's time doesn't work very well with nuclear weapons. They don't like to just sit there. If they have actual tritium put into them, then they're already used. The boosted parts are already gone. If they had lithium seven, like a lithium seven and tritium builders, they basically build tritium on the fly from lithium seven. That might be an issue, but still. Let's see. Other than countless super fun sites across America. Yeah, we have piles of that stuff all over the place, and nobody ever mentions those. Another topic, the polonium in the cigarettes. Well, yeah, polonium's in the cigarettes. Well, where does that come from? That comes from rainwater because rainwater has a uranium decay chain in it from radon. My mind's melted down. 220 2 3 4 5 6 226, yeah, 222. So radon is in the water, and that's what falls upon the plants and then dries, and eventually you get polonium 210 and then lead 208. So yeah, that's where all that comes from. Perfectly normal. That's actually natural. That doesn't come from anything man-made. Yeah. Helium's not good to have inside there, for sure. Let's see. Think about the criticality incident that happened in oh, criticality. Oh my god, dude, if you have two halves of a core, don't put them together. Like, what's wrong with you, man? You're causing a neutron flux by putting the two together. Basically, neutrons build up and they fly past one another, striking the atoms and causing fissions, and that makes more neutrons and so on. But they typically produce less than are needed to do anything. But you get them closer and closer and closer, and they start building up and energizing against one another. Basically, they start little miniature chain reactions, and you end up with a neutron flux, and you end up barbecuing yourself. That was an accident that should never have happened. Where radiation comes from camera lenses, gammas, alphas, betas, they all come from a thorium decay chain for the most part. Sometimes potassium decays occur in there too, but mostly it's going to be thorium. They're not really particularly dangerous most of the time. We are holding them apart with a screw. Oh, yeah. The dude that died from the neutron flux when he had the core, he was holding it apart with a screwdriver, and you wonder why he had a problem. Oh, but let me go ahead and put, by the way, the sodium 22 in this thing while we're just sitting here chatting about nothing. Let's throw this in here. Sodium 22, sodium 22, sodium 22. So let's stick that in there and see what it looks like, by the way, as a gamma spectrum. So let me jam this in place. This isn't normally where I test, so everything's kind of a little weird the way I have it set up. So let's go ahead and delete this. Delete this. No, don't do that. Do that. And then let's clear all our ROIs, and then let's go. And look at that. Look at that. So yeah. Let's see here. Wouldn't they be? Oh yeah. Cypher Fox. Yeah, that's absolutely true. The geometry of the core itself would be isometric after a period of time, and basically, if it even could initiate, it would be extremely deformed, and it would be a fizzle. It would blow itself a particular one way versus another because of the isometry, and as a result of it, it would tremendously fizzle. It would be, even if it did go off. So I doubt it they ever would. Any tips on radon and charcoal? Oh yeah, you asked me that earlier. I have never done a quantitative analysis of it. What you could do is use a Geiger counter with a charcoal filter, or you could take a paper filter and damn it, stupid Logitech, it has a button on it that I can press that makes it go mute. Why does it do that? That is so annoying. Very, very annoying. But anyway, that was the whole point of this first one. I wanted to get all these little kinks out, like the stupid button that just kind of does stuff. That way I could be better when I did my next one the next time. See what I mean? This was kind of a test. Let's switch to logarithmic view, by the way. There we go, logarithmic view. So basically, you'd want to take a. Did you hear anything about the charcoal, by the way, about the charcoal and the radon and the testing? Did any of that come through? Okay. Well, now that I know I lost everything, so basically, put to get back to the question about the filter, what you do is you can take like a filter and you can put like a cookie cutter piece around it and cut a specific small shape out of it, testing that same shape every single time. And this is through like an air filter or something. That way, you always use exactly the same piece, same sized piece of the filter from the same size piece of the air, of the filter. So it's like exactly always the same, tested under exactly the same conditions every single time. But the problem you have is you would only know that your radon has gone up or down. You wouldn't know how much, and the only way you'd know how much is if you could initially get a calibration or figure out pretty much what reading is equal to what dose rate or what activity. Most advanced technique, yes, cookie cutter, very advanced. I recommend Gingerbread Man. So anyway, you would have to have a calibrated source, and it might be possible to do that if you calculate the energies that you would be looking for from the radon. Helicopter going over my house. Oh no, conspiracies! A helicopter. And you had a calibrated source, you could figure it out. So you knew that your source is X number of becquerels. You know what percentage of those decays result in a particular gamma energy. So you could do it that way. You could limit yourself that way. But that would be kind of a that's something you could do. So what you could do, this is going to get kind of complicated. So let me just stop for a second and say that what I'm about to say is going to be a little more complicated. So hopefully you understand this. Hopefully you don't. I don't know. Take a cesium-137 sample, put something like copper or something in front of it, so all you're getting is the 662 keV photo peak. Calculate the change with and without the copper on using a gamma spectrometer, and then you'll know exactly how much. Actually, take a. That wouldn't work either. No, you're really screwed. You need a gamma spectrometer for it, really. You would need a gamma spectrometer. What you could do is you could calculate the dose rate from the cesium-137 and then calculate use that to kind of infer the dose rate from the 609 keV photo peak from bismuth 214. That's one thing you could do as an example. Let's see here. Don't want to blast my gingerbread man with radiation. Neutron capture? In a gamma ray emission. I don't know that it would. It could. It's going to depend a lot of how much what it's capturing. Uh, I wouldn't want to know what it was like to survive two kilosieverts. That's for sure. Oh my God. I don't know how much of his face he would have left. Remember, there's a difference between a whole body dose and an acute dose to a particular area. So, like, if I took your hand and blasted it with 2,000 sieverts, your hand might fall off, but but you would probably survive if the rest of your body didn't get hit by the radiation. So I get sidetracked so easily. The answer to the question, though, about the radon is that it's very complicated and involves basically figuring out how to determine the initial dose with respect to the initial reading. Yeah, if he's made by gingerbread, then he would be completely fine. I base that on absolutely nothing. So look at the spectrum, by the way. Not to get too off course and everything. Let's go back to linear view for a minute. Stop. Look at how sweet that is. That's one thing about the UCS30 I like. It's very pleasant looking, and you can see every part of it right here. So this right here is the actual spectra, the actual photo peak that comes from the decay of sodium 22 to neon 22. This right here is the 511 keV photo peak from the annihilation of antimatter. That's the Compton peak, Compton plateau, and backscatter peak that comes from that guy. You can see the same shape here is formed right here a little bit, but it's really hard to see it. If we zoom in, if we scroll up, you'll see the shape is pretty distinct. See that shape? It's the same shape you get here. It's hard to see. That right there is from the X-ray shielding, probably right there. And this is just some garbage X-rays. So let's quickly calibrate this thing. So energy calibration, 3-point calibrate. The units that we're going to be using are kilo electron volts, and we'll set it. We're going to go with this channel right here, which is channel, what is that channel right there? The centroid is 53, so that's 53. And the energy will be, energy's probably around 80 keV. Set this energy right here. Centroid is 358. Just click on it. It automatically fills it in for you. And that will be 511 keV. And this guy right here, just click it. Oh, look at how nice that is. You can type it in if you want, but you just click it, it works. And that will be 1274 keV. And then boom, look at that. Perfectly set up, perfectly calibrated, on the dot, ready to rock and roll. Go back to linear view. Look at that. Look at that. Beautiful spectrum. Well, thank you. Let's see here. Half of his head didn't. Or yeah, I wouldn't doubt it. My God, I'd be surprised he even lived. I have a minimal idea what's going on. Okay, well then let me explain this simple thing. Basically, gamma rays are being emitted from a radioactive source. It's emitting gamma radiation as a result of its decay. That gamma radiation is shooting off all over the place, and it's hitting a detector. That detector is taking that energy and it's producing little pulses of electricity. And the amount of electricity in the pulse that it produces is related to how much energy the gamma ray was. So high energy gamma ray, a lot of pulse of electricity. Low energy gamma ray, a little tiny pulse of electricity. This device right here is catching that, and it's saying it's like grabbing each one of those little pulses of electricity and putting it in a little tiny spot, like one of these little individual like little spots. And it does this based on energy. So this spot right here, for example, has 571 counts currently going in it, and that's only accepting energies at 764 keV. If you go up one, now it's at 585. It's one. I said that wrong. Channel 557 has 555 counts in it. Channel 558 has 562 counts, and so on. If we zoom far over here, let's go to this channel over here. That's channel 883. It's much higher energy, and there's only 1,524. Does that make some sense at all? It's kind of like the way how if you had a light spectrometer that produced a prism-like effect with all the colors of the rainbow, and then it produced peaks that rose up wherever a particular amount of light was stronger or lesser. So if you had a photo spectrometer and you pointed it at a blue light, then whatever the color is for blue would rise up in the spectrometer, showing that that's what it's detecting. BioNerd. Yes, that's correct. Oh yeah, BioNerd 23. Last time I heard she was mountain biking in, I think, South America. I see her every now and then on what is it, on Twitter. I haven't emailed her in a long time, so I might want to email her at some point and ask what she's up to. Um, are we measuring anything specific or just background? We're measuring sodium 22. Sodium 22. Sodium 22. So basically, if you've just tuned in, this is sodium 22. It emits this photo peak right here at 1,274 kiloelectron volts. So that's the gamma ray it emits when it decays from unstable sodium 22, which is radioactive, to stable neon 22, which is not radioactive, and emits this gamma ray. But it also emits positrons, which are antimatter. And yes, BioNerd 23 is awesome. And the antimatter decays rapidly, emitting gamma rays, and that's right here at 511 keV. That's what those are. In fact, if we go here and we go peak finder, it'll even tell you. That's pretty close. And then, of course, there's some X-rays in the background here. Yes, well, that's okay. That's perfectly fine. Let's see here. I need to go. Everybody have a good night. Well, good night, Jorah. So I hopefully everybody's having a little bit of fun. This is strangely, weirdly more fun than you would think it would be for me. I don't know why I find this so fun. Let's see what our background radiation looks like. Still not too bad. Device is at 40% power now, but still holding at about 0.05, so not too much. Let's read history just for giggles and see what that looks like on the spectrometer. This is in the Polymaster, by the way. Polymaster. Polymaster. Go, Polymaster, go! All right. And crash, Polymaster, crash! I don't know what's up with the Polymaster. It's normally pretty good, but like it hates this new laptop. Crash, Polymaster, crash! I choose you, Polymaster. All right, there it goes. Alrighty. Yeah, I know. I'm sounding a little Pokemon, aren't I? But anyhow, this, by the way, this detector is pretty neat because it can do a couple neat things. It can do Mossbauer spectroscopy. And Mossbauer spectroscopy is weird. Like, it's not going to work correctly because we don't have the right thing on it. You should be a TV series, Tom and his Polymaster. What's that, Polymaster? Has there been some evil bad person doing wrongdoings? Then we will need to go and right the wrongs, Polymaster. What is this, Polymaster? Is it a clue? Yeah, it would be that bad. It would get really terrible. What is that? Mossbauer spectroscopy? It's a technique of measuring the ultrafine the ultrafine movements of atoms, specifically things like iron, for example, using something like cobalt 57 or iron to I'm trying to say iron 55, I think, to excite them, and then it allows you to watch the hyperfine fluctuations in the crystalline structure of atoms. Mossbauer. Here, let me click it so you can see. Moss. See right here. Mossbauer. That's how it seems to be smelled. I sound like I said smelled. Spelled. It's German, like everything in nuclear physics. I'm not kidding you. Like everything in nuclear physics is German. I've never heard of it before, so thanks so much. Yeah, Mossbauer spectroscopy is interesting, and you can do it with the spectrometer I have here, but you need two things. You'll need to have something that produces that is able to excite the source, which is going to be something like cobalt 57 or iron 55, and you can get those both from Spectrum Techniques, and there's other sources you can get them from too. And you also need like a little vibrating motor thing that like spins the object. Like literally, it has to move, which I find bizarre, but that's how it works. I have never. I mean, I've done it, like I'm doing it right now, but I have no idea how to do it. Like, I have no idea how to do it. I'm all ignorant and stuff and don't know how. You can also do some other interesting stuff. So, like, you can do multi-channel scaling. So we're going to say that each 400 milliseconds will dwell in each channel. So go. See? Look what's happening. It's building up like a line right here. See the little line that's doing counts per channel. So it's getting 2,000 counts pretty much almost every single time. Now if I take the source and move the source like away, look at that. It drops. And if we move it even farther away, we've only moved it 2 inches. And look at the difference. This is useful because you can watch rainwater slowly decay over time using this. And then we put it back. And it goes right back up again. So anyway, this is some useful modes this thing has. What was that? Oh, voltage settings. So there we go. Oh, anyway. So there you go. Yeah, from this thing's perspective, it is. A huge amount of time. So why are people afraid of cell phones? Actually, I don't know why people are so afraid of cell phones. Because people are afraid of anything that causes cancer, and rightfully so. Cancer's like it sucks. I mean, I know people who've died of cancer. It sucks. I mean, we have a 1 in 4 chance of getting cancer, so that really sucks. And we of course spend like not enough money on figuring out what's wrong with it. I don't know why that's the case, but that's how everybody is. Nobody wants to spend any money on it for whatever reason. Um, So I don't know why they're so worried about it because there's so many better causes of cancer out there. Like, I don't know, better causes like good, but I mean more likely causes of cancer that are out there. But people fixate on certain things more than other things, and I've always thought that was a little weird. You'd think that they would be more interested in you would think people would be more interested in like fighting cancer and stuff, and but nobody wants to spend any money on it. We don't want to work on anything that'll help us. We all just want to spend our money on the stupidest stuff that will cause us the most possible troubles. Why humans are like this, I don't know. We spend all our money on wars and stuff like that. We never spend any money on like payer health or anything like that. I'm starting to get political here, so I probably shouldn't, but needless to say, I really think that we don't spend money on things that we should spend money on. That's just my personal opinion. So, okay. All right. Yeah, cell phone radiation is non-ionizing. Where do you buy lead bricks? I get them from rotometals.com. So let me just type this in here. This all sounds like one giant ad, doesn't it? Metals.com. That's where I get them from. Yeah, that's fine. I'm spending on that, but I would spend I would spend a lot if it were me, if I had like magical powers and could control everything, like if I just became like the dictator of the world. First off, I wouldn't want to be the dictator because that goes against my belief in a secular democracy. But regardless, let's say I magically became the dictator for a little while, I would put a huge amount of effort and money into hunting down a cure for cancer, increasing the amount of observation of the sky because of meteors that kill us all and everything, and trying to make sure that we can work in getting humans off of Earth so that we don't have all of our eggs in one basket. These are the things we should be doing if we really, 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 really cared about the human race. I would take away money from stupid stuff. I would put money on like solving things that kill people, getting rid of problems that are like that. Uh, I don't know. I mean, these are short-sighted things. Obviously, I'm not a political person, so I'm sure I would destroy everything and probably destabilize the world in about 30 minutes. Have you ever done alpha spectrometry? No, I have not. I've always wanted to. I just got an Eberline alpha spec, and I was nope. I do not actually, unfortunately. Yes, I did get a nice view of the Perseids, by the way. I got some nice pictures of them, which I haven't posted all of yet. But I have posted some of my Perseid pictures, so hopefully some of you have seen them. Yeah, I post a lot of that stuff on Twitter. If you don't follow me on Twitter, go ahead, but just let me give you a warning. I go into like rant fests over political crap when I'm on Twitter. I usually don't go into political stuff too much on YouTube, but on Twitter, I don't hold back. Probably you won't find my politics to be too terrible because like I don't think I'm like nuts or anything. I think I'm pretty darn rational personally, but obviously of course I think that everyone thinks they're rational, right? Especially people who aren't rational. But anyway, alrighty. So let's see. I think I'm that. There we go. Nice. So that's all. Let me see here. Yeah, that's true. A single meteor could kill us all. Oh, and as for the batteries, that's why you have a lot of batteries for your cameras. Keep lots of them. Oh, to answer the question about using a gamma spectrometer that uses something other than a photomultiplier tube, yeah, I have one of those right now. In fact, hold on, I'll show you one right this second. If it's been giving me troubles today, because it doesn't like this laptop, but this is the Polymaster. I've already shown this to some people. I'll show this to you again. This Polymaster does not use a photomultiplier tube. It uses a 4 cubic centimeter cesium iodide europium doped detector. So that's what it's using. And go ahead and connect. Bluetooth is on. It doesn't like this one at all. Carbon 14, you can get a sample of that from Spectrum Techniques. Come on. It doesn't like this laptop. Like, it works, but it doesn't like this laptop. So like, it might connect in a minute and it might work okay. Um, Come on. Uranium metal? No. I have no interest in uranium metal. I like uranium rock samples. Although, I mean, you can have one. They're perfectly legal. I don't have C14. Okay, connection was established. Well, then connect, stupid. Um, let's see here. I don't have carbon 14. I do have strontium 90, though. I have not for mapping rain, no. And yes, uranium rocks are purdy. I absolutely agree with you in that regard. All right, what's up with this? Let's try that again. I have no idea why that's like being annoying. Work, stupid. I would show you how this works. This uses a PIN diode and connects to the with that pancakes right onto the actual cesium iodide detector. And normally it works like a champ. Uranophane? Yeah, I think I do. And I think I have some uranophane. Connect, stupid. Okay, work. Why won't you connect? So basically, it has a lithium 6 iodide europium doped scintillator for detecting neutrons, and the other one is for detecting gamma rays, the cesium iodide one. I don't know why we're having this trouble right this second, but this thing has hated my laptop. Ever since I got this laptop going, it's hated it. It just like will not ever want to work with it. But anyway, so normally it works pretty well. It pulls a spectrum very fast, very clean, has a good response time. Photomultiplier tubes are nice and very versatile, but I really love the small and usefulness of pin diode based systems. I very, 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 very much like them. A cesium iodide is often connected to a pin diode. The problem with the cesium iodide is that it has a wider peak. It's not as narrow and not as high of resolution. I get about 7% resolution off of my nice, beautiful cesium iodide detector. Look at that. That's good resolution right there. That is good resolution for what it is. If you, I mean, this isn't the same as like a high purity germanium detector. This would be a single line if it were that. Guess it is not to be. But anyway, so let me see if I can get an example spectrum. I have some examples on my other laptop, and I'll move one over really quickly. So let's see here. Sample spectrum. Sample, SPE, right? Is it an SPE? So asterisk.SPE. Let me see if I can find a good one so I can show you guys what it looks like. Okay, here's a bunch of good ones. So let me find one that looks good. Here we go. Cesium 137. Okay, how about my Takamara lens? Yeah, let's use that instead. So this is a lens. This is a photography lens, and here's the spectrum for it. And we'll wait till that gets done freaking out there for a second. Uh, Oh yeah, I like my satellite videos 'cause I like doing astrophotography. Do you think that you ever wait, hold on, I'm trying to look back for do you ever think that telescopes they could? I hope not. I really have always kind of hoping that doesn't ever happen. That would be like terrible if it did. Really hope they don't. That's all I can say about that. I really hope they never do. I wouldn't call myself somebody who knows about those things. That's getting into like security at that point, and I don't know very much about that. I mean, like I probably guess that I might know a little bit more than this the average person walking down the street, but I'm by no means an expert at that. I know they rigorously check for that kind of stuff and look for it, and they try to stop people from doing that kind of stuff. I hope it never happens. Luckily, most nuclear power plants don't have a lot of digital stuff in them that can be affected by this. A lot of them, it's kind of funny, they get in trouble all the time for having such old equipment, like antiquated equipment. But sometimes that 1950s, 60s, 70s equipment might be, part of what's helping them because a lot of that stuff has like manual knobs and buttons and stuff like that are just direct electrical connections. And then they have modern day systems over top of it that observe. So you could probably make one think something bad's happening, but it wouldn't stand up to scrutiny when somebody ran down there with a detector and started looking. So that's probably one really helpful thing right there. That is a very dangerous thing. That's why, honestly, I don't think that reactors should be connected to the networks in any way, shape, or form. And I think, honestly, stuff that's connected to them, like, equipment that's put in, should be extremely carefully analyzed before it's put in place. Yeah, I've done security stuff before, like computer wise, because that's I do computers for a living, but not that type. All right, so just let's take a look at the spectrum here for a second. This right here is a thorium spectrum, so energy, and this is using a PIN diode and a cesium iodide detector. What about national disasters? What about natural disasters in Fukushima? Well, the problem with that, though, is that's not a matter of like, it's an equivocation fallacy to equate ancient technology that people can't get into with the internet with, for example, the Fukushima, for example. What happened there was it ironically probably would have taken either the tsunami or the earthquake, but the problem is it took both. That was poor design. Chernobyl was the result of people engineering the thing into breaking. They didn't mean to. They were trying to set up a new system for using the power down of the generators to actually run the cooling systems, and they kind of blew it all up themselves. Um, Fukushima was poor planning in it with the concept of the water and the tsunami. Why that was never thought of, I don't know. Um, how to see satellites video really debunk? Yeah, I don't know how flat Earth people can still exist to this point. I don't even understand how you can believe in a flat Earth because it's so demonstrably wrong. You can literally just get on a boat and go see that it's not real as you slowly go over the horizon with your big telescopes. You can watch the cities and towns behind you disappear. And this, I mean, you look up and you see the satellites go over with your own freaking eyes. You can, with a really powerful telescope, you can actually see like the shape of the International Space Station. Like, so since a satellite is an object put into space, or actually a object in space that orbits us, it doesn't have to be man-made. But if I mean, how would you describe how would a satellite conspiracy theorist? There's a lot of people that think like satellites are fake. I don't even understand that. How do they explain the things? And if they're like, well, the government put those up there to pretend that they're satellites, well, they're still satellites then. So like, I mean, how do you argue with that? It doesn't even make sense. Oh my God. Yeah, you said that thorium has a low Barnes radius so that it would never become a viable fuel. No, no, that's not right. Um, yeah. So basically, yeah, I love ISS. So International Space Station. So yeah, thorium itself doesn't make a good fuel. What it does is it accepts neutrons and then it turns into a form of uranium, which is a good fuel, which then does its uranium thing. So like it's a breeding material. It's what's called a fertile material. So it accepts neutrons and then it spits out uranium atoms. You have to zap it with neutrons to get it going in the first place. So it's not like if you cut the external neutron source off, it just cuts off. That's why the fact that it doesn't by itself do anything is part of what makes it so useful. The neck monitoring site. Oh yeah, I get annoyed by fearmongers because they have a tendency to bring up false issues, things that aren't real, and then people turn them into conspiracies and stuff, and that detracts from real, actual problems. We have enough real problems in the world without inventing them. It drives me nuts. So anyway, here's the spectrum right here, and you can see the peaks for thorium. Look at those nice, happy peaks. Look at them, and this should be one at 5. This should be 580 something. Yep, look at that. There we go. Look at that. And we'll go to logarithmic, and you'll see some stuff over here too. Look at that. We have almost a 4, look at that, almost a 4, 3.7 MeV range on this little tiny itty bitty detector. It can barely pick it up. It's so small. How does accepting neutrons change the atomic number? Oh, well, if it accepts a neutron, then it goes up by 1. So, basically put what it boils down to is the actual atomic number is the number of protons. So it doesn't change. If I said number, I mean I always say number. I mean weight. Atomic weight is what I'm referring to. So like, let's say, let's take what would be a good one? Uranium 238. Uranium 238. Its atomic weight is 238. It's not exactly 238. It's 238 point something or other. It's 238, but its atomic number is 92. All uraniums are 92. Every single possible version of uranium that could ever exist is 92. That's the number of protons. The number of neutrons is higher than that. I don't even remember the number of neutrons. So let me just do the math really quickly here. 238, so uranium 238 minus 92 was 146 neutrons. So if it captures a neutron and then becomes 147 neutrons, then it would become 147 plus 92, which would be 239. Does that make sense? There's a little nuclear plant right now above, of course it's above a fault line, because that's where they seem to put every freaking nuclear reactor for some idiotic reason. Yeah, I would never put one there. Was that thorium metal? Oh no, that was thoriated glass. That the spectrum you're looking at is thoriated glass, which I get a kick out of from a little glass lens. Um, how does thorium? Oh, I don't remember the exact thing. Let me just type it in here and see. 232 to here we go, to uranium 233. That's where it is. So basically, it probably beta decays most likely. Let me look. It's probably a beta decay, almost assuredly, because a neutron can beta negative to a proton. So let me just double check the decay. I'm looking it up right now, so I'm just not lying and being like, oh, I had it off the top of my head. Yeah, I'm looking it up right here. So shows it on Wikipedia here. Neutron plus 232 becomes thorium 233, which beta decays to Pa 233, which then beta decays to uranium 233. Okay, that makes sense. Let's see. We could probably look that up too. Here's a place to go. New DAT. New DAT. So this is a governmental. It's super useful. New DAT. And let's go to thorium 232, right? So thorium 232. My cat's making screaming sounds. That's lab assistant Mew. He's angry and he wants to be doing science. Lab assistant Mew? Can everybody hear lab assistant Mew? Lab assistant Mew? Lab assistant Mew? I don't know if you can hear lab assistant Mew. Yep. Well, Mew is in the micro symbol. But yeah, basically. He screams because he hears science, and he's very angry that science isn't occurring with him. He thinks he should be involved. So this is like a government site, so we can show it like legally because they don't care about copyrights of the government, which is one nice thing. So let's zoom all the way. New DAT is the awesomest thing ever. So anyway, this right here is thorium 232, and it accepts a neutron. And let's see, where should that put it up? That should pop it right up here to well, actually, that should go to thorium 233, and then that beta decays into Pa233 right here. So basically, a neutron turns into a proton, same weight, same atomic weight, but the Z number goes up by one, and then that pops over here again by a neutron turning into a proton. A neutron turning into a proton. So neutron to proton, and you end up with this guy right here, uranium 233. Does that make sense? So that's where you get your fuel from. And 233 is fissile, 233 is fertile. That's the terminology. But normally 233, thorium 233 would be a very useless fertile material because it needs to constantly get hit by a neutron source. But that's good. That means when your reactor gets hit by like a tsunami, Godzilla, small meteorite, and a earthquake at the same time, then like it doesn't go Chernobyl because it shuts off pretty soon because it stops making the fuel which it has to make on the fly. Now you still have decay radiation and you still have decay heat, which is a bit of a problem. This is why I prefer fusion reactors, because a fusion reactor, when it cuts off, it just cuts off. That's it. You're done. Worst case scenario, if you're using tritium, you could get a little bit of tritium loss, and that's like makes the room that you're in maybe a little bit slightly hazardous, but not by much. I mean, really, there's not going to be very much in there. That's why fusion is by far the best alternative. Why we don't use fusion now, I don't even know. It's just idiotic. People come up with all these stupid reasons for not using fusion, and it just drives me nuts because like they're usually really stupid reasons. By the way, let's go to. But if you wanted to actually look up the spectrum that we did of sodium 22, we could do it right here. So let's go down to sodium 22. Sodium. Here we go. Sodium 22. Well, pretty close. We'll get down there. So here we go. Sodium 22. There. Center it. There's sodium 22 right there. And that's turning into stable neon 22 right here. Radioactive cookie puzzle? Nope, not at all. I was ignorant. I was done no. So let's click on decay radiation and see what we get. What do we get? All right, so what do we get right here? It's all nice and sided and stuff. You get the betas here with your betas, your full continuums and Q values and stuff, and all these and auger values and all those. But here's what's really important. Where's the gamma ray? Gamma. Here we go. Right there. That's the gamma energy right there. And then you get an annihilation peak right here. And then you get the K alpha 1, K alpha 2 for X-ray emissions fluoroscopy. Yay! Look at all that cool stuff. It would help if they had a working fusion reactor capable of power generation, which is they're still trying to make. Yeah. But they could spend a little bit more money and probably do it. I like how you like radioactive materials. Well, I like how I like radioactive materials too. I like them within reason. I mean, I don't want to like expose myself to them all day long. I'm not like a nuclear file. It's just I think they're very interesting. I mean, look how neat they are. They are kind of neat, aren't they? Anybody else think they're kind of neat? Maybe. Of course, you find them neat. If you didn't find them neat, you wouldn't be here, right? Haha. But anyhow, for everybody who wasn't looking earlier, let me go back. That's a sodium 22 spectrum that I've been forming. Look how nice it is. Look how nice. And look, you see, if you look at the little box, you can actually see the counts going. Look at the net counts just rising. Let's go to the 511 one. That's going to be even higher. Look how many. It's over at 1.8 million counts and rising. The reason it says gross and net is it's guessing what its background should be. So I called up the developers for the software for this and asked them what they do. They do a 3-point smooth from 2 or 3 points on either side of the region of interest, and that's what they use to calculate the background. You have for 4 radioactive cookies, an alpha, a beta, gamma, and a neutron emitter. You have to eat one, throw one away, hold one, and put one in your pocket. What goes where? Well, the neutron gets thrown away. The gamma goes into my mouth. The beta emitter goes into my pocket, and I'll hold the alpha. I might put the alpha in my pocket and hold the beta. Well, yeah, on the one side, nuclear power can be dangerous, but on the other side, consider this is the warmest year we've ever had. I know that there's people out there that don't know anything about science that claim that climate change isn't real, but it turns out that all of the scientists, when I say all, it's not all, it's like 99.9999999999999%. There's like three people that don't, but basically all of the scientists, and when I say all of them, I mean like there are doctors, there's probably a doctor someplace on earth who's like a doctor who actually thinks that fatty fast foods don't cause heart disease. I'm sure there's one. I'm sure we could find one. But basically all doctors agree that fatty foods cause heart disease. I'm talking like McDonald's burgers. I'm not talking about olive oil stuff. I'm talking about like burgers and stuff, okay? So basically all climate scientists think that we have something called anthropogenic climate change, so man-made climate change, and it's all over the place. Looking at I like pause because I'm looking at stuff. So basically, put with climate change as bad as it is, we need electrical power. Let's face it, we all like to use hair dryers and all kinds of weird stuff. So we need electrical power, and we don't have a fusion yet. So what are we going to do until then? We have to figure out some way to generate electrical power that isn't killing us with greenhouse gases. And unfortunately, right now, fission's the best deal in town. I don't like fission reactions. I'd like to do away with them personally. I'd like to quickly switch to thorium and then fusion. But no matter what, we got to stop with all this coal and everything like that. It's killing us. And if you don't realize that, look at how hot it is. Look at how like entire Pacific islands are going underwater. My God, they actually are. It's not even like a joke anymore. An entire species just disappeared as a result of global warming. There's no joke. They know for a fact. It was here, now it's gone. And people that are like, oh, were you there to see it? Yes, we were there to see it. It's gone. That's actually happening right now. We're all slowly dying of it, and we don't even know it. Third world countries are going to be the ones that get it hit first. Millions will be dying. We will be sitting back in the United States sipping coffee and playing with our spectrometers, not caring as millions die. They already are. The entire Middle East. You want peace in the Middle East? Well, it'll be peace in the Middle East pretty soon. Within 100 years, it'll be uninhabitable, so there won't be anybody there to fight. There's going to be some serious problems, and we don't take this at all into consideration. I mean, I think the nuclear reactors, fission reactors, are very dangerous sometimes. They can be, especially since we seem to always build them on fault lines and stick everything right beside the most dangerous, idiotic locations, and we build them to just slightly better than what they need to be. And I mean, we do the wrong thing, but they could be made way safer than we are, and we've got to do something because climate change is upon us. We've already passed the safety margins where we could turn it around. At this point, we're moving into like the serious danger zone, and nobody cares. My God, we still have politicians that are out there arguing that it's not true. We had a stupid politician in the U.S. who threw snowballs and then claimed because he had snow in his hand that there wasn't global warming. That's like a person who has a week left to live, lying in a medical bed, dying, and looking up and saying, oh, I breathed and my heart's beating, therefore I'm alive, therefore I'm not dying. That's the level of stupidity that is. But yeah, yes, but radiation is the most dangerous thing that human. No, not really, I don't think. Nuclear weapons are. Nuclear weapons are. Nuclear war. If Russia and the United States got into a nuclear war, we wouldn't kill everybody on Earth, but we would destroy basically everything. Everything we know of a civilization would be destroyed. I mean, you would never kill everybody off. There'd always be people. We wouldn't be back in the Stone Age per se, but you could lose a large percentage of the human population just like overnight. It would not look like Fallout 4, which is just nothing but pure fiction, or Mad Max. That isn't what it looks like. It would be nice and green and fertile afterwards. There's no people. It would be a lot less people anyway. So like, yeah, nuclear weapons are extremely dangerous. Oh my God, the fear. I mean, the countries have these devices now where like Russia's dead hand system. They're like, oh, look, if we're all gone and we've been completely turned to glass, we can still launch a retaliatory strike. Think about that. Think about the systems that can do that. How dangerous is that? That's extremely dangerous. Reactors melting down. Look at that. Like we've we're still all living. There might be some increased cancer risk, yes, but compare that to a nuclear war. That's dangerous. You want to talk about dangerous? Hair trigger nuclear launch capability, destroying the whole world within 90 minutes. I'll tell you, that's dangerous. Now, if we're talking about, well, hold on a second. If you're talking about, somebody wrote Russia in Russian. Interesting. Russia. So yeah, if we're talking specifically about power sources, though, have you ever been to Trinity? No, I have not been there. I'd like to go there. If we're talking about power sources, though, if we want to combine it to that, Then power sources, that's a good question. I don't think nuclear power is. Because the actual attributable sources of cancer to nuclear power are not that many. And even if you take like the really high levels, like the people that get out there, the doomsayers, and they're like, a million people will be dead. You'd also have to do an analysis of how many people will die of lung cancer from coal. Lung cancer affects thousands and thousands of people every single year. Not all of it. In fact, plenty of it actually doesn't come from smoking. Smoking is, yes, that's correct. Yeni Paini Mayu Peruski. So I like to listen to you ramble. You are a rational human. I'm not rational about everything, and I'm wrong about many things. In fact, there are subjects that I am very wrong about, and I will not get into them because I'll just be wrong, and I'll know I'm wrong, and then I'll be too much of an ass to like not admit it. So yeah, don't put me down for common sense. I'm common sense. I think about some stuff, and I know that I'm wrong about other stuff. At least I admit that I know I can be wrong. Coal has released more radiation. Oh yeah, I did a coal a spectrum. Coal is quite radioactive. In fact, let me see if I can find it. Let's see if I can find my coal spectrum. Anti-proton.com. Coal. Like I did a spectrum of coal. Coal is radioactive, and that gets in the air and we breathe it. Um, where is it? See, I need to redo my website. I can't find anything on it. It's my own fault. I'm stupid. Gamma Spectrum. I am dumb. I is our dumb. All right, so here we are. These are gamma spectra, but look at this. That's funny. That's my picture. These guys took my picture. I found this picture on the internet randomly when I was looking, and I was like, why is my picture on these guys' webpage on the Center for Nuclear Science and Technology? So I contacted them. And I was like, really? And so I said, you can keep it, but you have to copyright it. I just want my name on there. That's all I want. I'm an attention whore, and I want my name on it. That's it. So they're like, okay. So they put the name on it, so we're good. I just got a kick out of that. Like I found my picture like randomly on there. Like where's this YouTube? I did a coal spectrum. Somewhere there's a science. Somewhere there's a coal spectrum I did, and I showed that there was uranium in it. So who knows where that is? But what am I clicking on? Go away. Stop showing copyrighted stuff. Uh, if you ate uranium, it would kill you first. Probably the heavy metal. Supernova. No, you would not like to see that. You think you would, but you wouldn't. Trust me on that one. If you ate uranium, probably the uranium is chemically toxic, very chemically toxic. Porcelain, sure, I'll do porcelain. I got to go find some porcelain to do. I've got some sitting around someplace. I've got a whole bunch of random stuff. Your toilet seat will work for that one. Yeah. You can lead is extremely toxic, and so is uranium. Just as being toxic, mind you, not as being like radioactive. Uranium's toxicity would increase your chance of cancer, but its chemical toxicity would kill you far before the other did. And that's the thing a lot of people don't understand. That's the actual radiation. Uranium is only weakly radioactive. I know people think it's like so dangerous, but I mean I'll prove it to you. Like I will now prove to you that uranium is only weakly radioactive. Watch. I will prove it. All right, so here we go. All right. Specific radioactivity of uranium 238. Specific radioactivity of cesium 137. Let's see how much radiation you get off of a 1 gram of each of these two substances. 12.44 thousand decays per second per gram. 12.44 thousand. 3.214 trillion. Trillion. And just in case we're still not sure, how big is one number versus the other number? A billion something times bigger. A billion. Oh my God, a billion. And look at radium 220. Oh my God, look at radium 226 is even worse. Radium 226 is really nasty. Like or how about this? How about N14, nitrogen 14, or something even worse? Or your yeah, ooh, let's see, in 16. N16. There we go. Oh my God. 3.615 times 10 to the ninth power terabecquerels. Oh my god. That's ludicrous. Oh, no problem. See you later. Chicken trash. That's a funny name. So there you go. Yeah, yeah, I wear gloves for the lead and stuff, not the radioactive stuff. It goes right through the gloves anyway. I like how you like science. I like how I like science. Uh, yeah. So, I don't know which one the last one was. I did in 16, so nitrogen 16. I did nitrogen 14, which I accidentally said 14, which is not radioactive because I'm dumb. And then that was cesium 137 was another one that I did. Everyone should like science. Only 15 viewers. That's okay. We'll do more next time. I like go on and on and on for the next. I'll spam like Twitter and stuff the next day or two until I'm ready for the next one. The next one's weird. I'm gonna do a put together actually a plastic model. I thought that would be funny to do. Put together a plastic model, and it's a plastic model of nuclear missiles. I thought that would be funny. So I'll do that one and see how amusing that is. I'm going to do a few more of these because I'm actually enjoying this. My God, it's like 10:33 and I'm still doing this. I have no idea why I'm doing this, like for this long. But I'm going to do more of these. This is super fun. I don't know why I'm enjoying it so much, but it's super, super, super fun. Oh God, I just remembered. I left a plastic cup full of water in the freezer like 4 hours ago. Yeah. 3:36 a.m. 3:36 a.m. 10, 11, 11, 12, 12, 1, 1, 2, 2, 3. So you're in middle of Europe, like probably Russia. Uh, and nothing wrong with a vacuum-based Geiger counter, vacuum tube. I have a couple of them too sitting around. I've got three of them sitting around me right this moment. But anyhow, so wow, that's really going. So let's get rid of this spectrum for a second, and let's introduce something different into the fold. Let's introduce cesium 137 again, just for anybody who hasn't already seen what that looks like. Let me get that to like fit in there. All right, now we'll kill this and let that rise slowly. There we go, cesium 137. Cypher Fox. Oh, I stay away from the X-ray generators. UK on the spot, close enough. Okay, UK. Yeah, I'm wrong about that. I wouldn't call Europe and I wouldn't call Russia and UK too close. I love UK, by the way. I like Edinburgh the best. I love going to Edinburgh. What sparked my interest in science? That was two sentences put together. Um, I don't know. I've just always loved science. Um, just always loved science. I like geology. Okay, I like all sciences, but my main focuses are astrophysics, and astronomy, nuclear physics, computer science is what I do for a living, pretty much, and let's see what else. I love mineralogy, so um, I'm thinking about doing one of these videos where I program, by the way, and teach you guys how to I like sit down and just write a program out in like Java or something, and that could be useful too, because like people could like that maybe. Like I would be like class meow, end class meow, public static void main string args blah end main method system dot out dot print line meow. Done. Java program. Uh, so yeah, oh, I wouldn't be worried about something bigger than a supernova because you wouldn't even know, you'd be toast, and everybody else within a few parsecs of you. So yeah, I thought about programming one would be kind of neat. I program in a bunch of languages. Java's my favorite one, but I do others too. I might check out those videos as well. The big thing I haven't been doing recently is I haven't been checking a lot of my YouTube comments, and mostly it's just because I get so much trash. I like get good comments from good people, but I get all these freaking morons all the time too, and it gets annoying after a while. I guess I've just gotten sick of fighting them, like this, the stupid ones, because I get them all the time. Like, let me look at a comment I'm getting right this moment here. I just got a comment. Let's see what it says. Um, oh yeah, that one wasn't dumb. That's odd. I'm like, look at a comment and it wasn't dumb, but it's true. What's my favorite movie? Oh God, I actually put that on Twitter recently. I like anything from Miyazaki, such as Kiki's Delivery Service, and for example, or Howl's Floating Castle or Nausicaa. I like The Fifth Element. I like all Star Wars. I like all Star Trek. I like Contact. That's another good movie. I like Ghost in the Shell. Bicentennial Man wasn't bad either. Metropolis, good movie. Yeah, I wish I had that many freaking subs too. That would be awesome. But then basically I wouldn't be able to deal with it. It's hard to manage that many. Even just the few followers I have, it's a lot. So it could be a bit of a pain sometimes. I've been spending a lot of time recently writing my books. I'm in the middle of writing one right this moment. I was thinking about maybe doing a little class on how to write a book. So since this will be my third novel, so I mean I'm not really an expert, but I'm not like a complete amateur. And I mean, I got 180 book sales last month, so I mean, they're selling. No, I don't think I've ever seen Cypher Fox's videos. Maybe I have, maybe I haven't. So I will go and take a peek at that at some point here and see what they look like. Here you go. Look at that. By the way, cesium 137. Here's the logarithmic view. So what do we have? We have, let's hold on, stop for a second. Clear regions of interest. We have the 32, come here, 32 keV peak right here. That's from X-rays from barium 137. Then we have the X-ray backscatter stuff here. It's not backscatter. It's X-ray fluorescence from the lead shielding. This right here would be backscatter. Now we have a backscatter peak. X-rays that are gammas that are reflected completely backwards. They just fly right backwards. We have the entire Compton edge, which is this. The entire Compton plateau. The Compton edge, which is, stupid thing, clear ROI. This is the Compton edge. This is the Compton plateau. This is the primary photo peak, and this is some pile up. So this is like, what would that take? There. That's just garbage that piles up for the most part. That's that. Oh yeah, I'd be a billionaire if I had that many followers, that's for sure. I've made a little bit of money with my ads, but like it's pocket change at best, 20, $30. You don't make very much. I love my video indicator. It's like the amount of money that we suspect that you will make this month is $400. The amount of money I made this month is $4. I mean, it's so far off. I don't even know why it even suggests that. So, yeah, push your videos all you want. Shameless promotion is perfectly acceptable. So there we go. Actually, Fox to a degree will have something to do with my next book, my Ember Book 3. The Ember series it will involve a fox to some degree, so you might get a kick out of that. Go have to drive 9 hours to Lubbock tomorrow for the fall semester. Suck. Have a great night, y'all. Um, oh yeah, thanks a bunch. So hopefully you had fun. Not sure where Lubbock is, but still. Au revoir. Do svidania. Spokojnej noche. Sayonara. Um, Hagone? I think that's proper Navajo. Hagone? What reflects gammas? Anything. Gammas bounce off of normal matter to some degree, but that's only if they perfectly strike it. They usually fly right through. And they attenuate a little bit. So think of bullets and trees. So if you have a bunch of trees and you shoot a bullet from a gun, the bullet flies forward and it may fly right through the trees, never hitting any of them. It could also deflect off a tree, continuing more or less in the same direction, but at a slight angle because it deflected a little bit and losing some of its energy each time it makes one of those collisions. Or it could hit a tree. Literally, bullets can actually hit trees and actually bounce. They can do that. They usually go into the tree, but they could bounce and reflect back, or they could completely be absorbed by the tree. Radioactive man? Nope, never. So, yeah, that's what happens with gammas and X-rays. Gammas and X-rays are the same thing. They're both photons. The difference between a gamma and X-ray is what formed it. And they mistakenly teach you in school that lower energy is X-ray and higher energy is gamma ray, but it just happens to be that lower is usually X-ray, higher is usually gamma ray energy. But the actual formation is what causes the difference between the two. The Compton Plateau. I don't know if I have or not. I'm pretty sure I did a Compton scattering video one time. I might have to do a Compton scattering video at some point and actually explain how that works. Because Compton scatter is kind of an interesting thing. And cesium-137 is probably the best radionuclide of the exempt quantities to use for showing it. Don't think I've ever seen that, but bullets can do weird things. Like, for example, when a bullet hits the ground, it has a tendency to run across the ground as opposed to like bouncing. Bullets can do weird stuff. In fact, the geometry and the physics of high energy impacts are quite interesting to look into. Things don't always behave the way you think they're going to behave, especially at high energy levels. And the same goes for radiation. It does strange things you don't expect. By the way, I love the fact that my background radiation dose right this second is 0.06 microsieverts per hour. Here I am sitting beside these two little exempt sources and they're like doing nothing. Like I barely even detect them. So here I'm going to take my, let me get this thing going. I'm going to get my spectrum continuing to form. There it goes. And I'm going to throw my sodium 22 sample nearby the detector and see if it picks up. So there it goes. See if we see a difference in the spectrum. You should. Oh, will electrons reflect? Yep. 0.12. Yeah, that's probably right, but you're probably getting that off of a Geiger counter. They tend to read a little higher than the Polymaster. I would say you're getting that off a Geiger counter. Oh, beta gamma X-ray, yeah, you're getting that off a Geiger counter. Well, you could think of, I wouldn't really call them a subtype. Strong nuclear force interactions are what typically produces gamma rays. So whenever the nucleus does something, or for example, if two electrons combine together and annihilate one another, weak interactions, typically in electromagnetic interactions, produce X-rays. There's nothing wrong with the cheap GMC 320. It's a nice Geiger counter, and I love the sound it makes. It makes that little ticking sound, and it kind of looks nice too. So I wouldn't knock your 320. I think they're neat. I always thought about getting one. Look at how it's changing. The spectrum's changing. So you've got this peak right here beginning to form, right there, and that's the 511 keV annihilation peak. And then over here you have the 1273, 1274 peak from the primary decay. So that's all as a result of the sodium 22. Yay, sodium 22. All right, well, I'm going to probably call this end to this pretty soon. I'm getting kind of hungry, and it's been going on forever. But it is super duper fun nonetheless. Everybody I put out a Twitter thing for this, and everybody wanted the nuclear missile plastic model kit, so I'll be doing that one next time. So this is like my warm-up one, but I'm going to do more of these. I think instead of just doing my video logs that I was doing, like I got mixed reviews in those. You know, like I mentioned this one feminist topic, and that just went to shit. Like Everybody didn't understand. They thought I was like a third wave feminist person. You know, the ones that like attack you for everything that you do, and like they like man hate and stuff. No, 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 I don't do that. But somehow that got misconstrued. So like, God only knows. I'll do more of these though. Maybe this will be better. People seem to like this. But anyhow, so yeah, I think I'm pretty much gonna end it for now. By the way, for the record, I got the idea of doing this from watching the Find Chaos group on you know, they do the comics and stuff. They're also the people who made the covers for my books. When they did their live screening, they were like basically drawing the entire time, and I spent like 3 hours watching that. It was way too much fun, so I kind of got over the top. Next time I'm gonna have to drink a bunch of beers or something too, so it can get even weirder, and I can say even stranger things. So this has been Tom from anti-proton.com. What am I going to eat? A salad, most likely, and then maybe some tuna. I eat pretty healthy food for the most part, although tomorrow I'm probably going to pig out because tomorrow I'm playing Dungeons and Dragons all day long. This has been Tom from anti-proton.com, and catch you guys on the flip side as soon as I actually hit the button that does that.